In the vast darkness of the cosmos, where galaxies swirl like celestial hurricanes and black holes dominate the centers of nearly every massive system, one galaxy stands out not for what it contains, but for what it astonishingly lacks. A2261 BCG, a colossal elliptical galaxy over 10 times the size of the Milky Way, appears to be missing its central supermassive black hole. A cosmic mystery that has baffled astronomers since its discovery. This silent void at the galaxy's core defies everything we understand about galactic evolution, challenging the very foundations of astrophysics and opening the door to a universe of questions more massive than the black hole that should be there. Imagine a galaxy that stretches across more than 1,000,000 light-years, one of the largest ever observed, residing in the heart of a galaxy cluster some 3 billion light-years from Earth. A 2261 BCG is not your average galaxy. It is what astronomers call a brightest cluster galaxy, or BCG for short, which means it dominates its local group of galaxies not only in size but also in mass and luminosity. These galaxies typically have one feature in common: a supermassive black hole embedded at their cores. These black holes, often millions to billions of times the mass of our Sun, help shape the formation of galaxies, anchor their centers with gravitational might, and dictate the flow of matter and energy across vast cosmic scales. So when scientists turned their telescopes toward A2261 BCG and peered into its enormous, luminous heart, they expected to find a monster lurking there, an ultramassive black hole, perhaps one of the largest ever seen. But they didn't. Instead, what they found was nothing. Nothing in the middle. Nothing at the core. Nothing where there absolutely, positively, without a doubt should have been a gravitational behemoth. The central region of A2261 BCG was unusually diffuse, flat, and empty, a gaping void in place of the intense gravitational well expected of such a galaxy. This bizarre absence opened the door to a realm of speculation, theory, and fascination. Could a black hole somehow be ejected from a galaxy? Could such an event explain the diffuse core? What does this tell us about the dynamic processes that shape the universe on galactic scales? And what, if anything, does it mean for our understanding of how supermassive black holes and galaxies co-evolve? To grasp the full magnitude of the mystery surrounding A2261 BCG, one must first understand what makes galaxies tick. At the core of most large galaxies lies a supermassive black hole. Our own Milky Way has one, Sagittarius A, weighing in at around 4 million solar masses. But that is considered a modest black hole by cosmic standards. Some galaxies host black holes weighing in at billions of times the mass of the Sun. These black holes don't merely sit idly in the middle of their host galaxies. They interact dynamically with the stars, dust, and dark matter surrounding them. They accrete matter, eject powerful jets of radiation, and regulate star formation. Their mass is so deeply intertwined with the mass of the galactic bulge that astronomers believe the two evolved together, linked through mechanisms not yet fully understood. This correlation, the so-called M-sigma relation, is one of the most profound in modern astrophysics. It implies that the formation of a galaxy and its central black hole is not a random pairing, but rather a codependent process governed by the physics of gravity, gas dynamics, and cosmic feedback. But in the case of A2261 BCG, that link seems to have been severed. The M-sigma relation does not explain the absence of a black hole in a galaxy of such immense scale. So how did this galaxy end up missing its central black hole? The first clue that something was amiss came from the unusually large and flat core of the galaxy. In most giant elliptical galaxies, the core is compact and dense, lit up by a tight swarm of stars orbiting the central black hole. But A2261 BCG's core is unusually large, nearly 10,000 light-years across, and remarkably flat. It's one of the most diffuse galactic cores ever observed. This diffuse core suggests something dramatic may have happened in the recent history of the galaxy, something that may have displaced the black hole, or even expelled it altogether. Such a scenario, though seemingly implausible, is not entirely outside the realm of theoretical possibility. One idea is that A2261 BCG experienced a massive galactic merger in the not-so-distant past. When two galaxies collide, their central black holes spiral toward each other and eventually merge. As they coalesce, they release a torrent of gravitational waves, ripples in the fabric of space-time. According to Einstein's general theory of relativity, if these gravitational waves are emitted asymmetrically, the merged black hole could receive a powerful kick, a recoil velocity that could potentially eject it from the galaxy altogether. This phenomenon, known as a gravitational wave recoil, has been modeled in simulations, and although it's exceedingly rare, it's theoretically possible. The ejection velocity would need to overcome the galaxy's gravitational binding energy, which in the case of A2261 BCG is immense. But if the merged black hole received a recoil velocity of a few thousand kilometers per second, it could, in principle, be flung from the galaxy entirely, leaving behind a diffuse core and a gaping absence where the gravitational anchor once lay. If this happened in A2261 BCG, it would be one of the most dramatic black hole ejections ever observed, offering the first real-world example of a process only predicted in simulations. But to validate such a theory, astronomers need evidence. Could the black hole still be nearby, hiding in the galaxy's outskirts or lurking among its halo stars? Could it be revealed through a careful search for telltale X-ray emissions or gravitational lensing effects? So far, the search has yielded no conclusive answers. The Chandra X-ray Observatory, one of the most powerful tools available to hunt for black holes, found no sign of the X-ray signature typically emitted by a feeding black hole. The Hubble Space Telescope, with its high-resolution imaging capabilities, has scanned the core and surrounding areas of A2261 BCG in search of any unusual features that might betray the location of a displaced black hole. Several compact clumps of stars have been identified in the core region, possibly remnants of a recent galactic collision, but none have revealed the presence of a supermassive black hole. One possibility is that the black hole is hidden in one of these clumps, too faint or dormant to be detected by current instruments. Another is that it truly has been ejected into intergalactic space, now drifting alone, invisible, and unreachable, like a cosmic phantom. Adding to the intrigue is the fact that A2261 BCG is not alone in challenging our expectations about galactic cores. Other galaxies with similarly large, flat cores have been discovered, suggesting that black hole ejection events, while rare, might not be entirely unique. Could it be that the universe is littered with rogue supermassive black holes, wandering the void between galaxies? If so, what does that mean for the fate of the galaxies they once inhabited, and for the cosmic ecosystems they helped shape? Each new observation of A2261 BCG deepens the mystery. Rather than resolving the paradox, new data seem to only complicate the picture. The lack of a central black hole, combined with the massive size and luminosity of the galaxy, raises serious questions about how it formed and evolved. If a galaxy of this scale can exist without a central black hole, or with one that has been violently expelled, then the models we use to understand galaxy evolution may need to be revised. Perhaps black holes are not as essential to galaxy formation as we thought. Or perhaps we've only just begun to uncover the exotic, violent, and unpredictable behaviors that black holes can exhibit. Yet, as with all great cosmic mysteries, the answers may lie not just in the specifics of A2261 BCG, but in the broader implications it holds for astrophysics, cosmology, and our understanding of space and time. The study of A2261 BCG is not merely about locating a missing black hole. It is about testing the limits of our scientific models, confronting the anomalies that defy our expectations, and allowing ourselves to be humbled by the vast unknowns that still populate our universe. If one were to stand in the center of A2261 BCG, hypothetically speaking, as any such presence would instantly be annihilated by cosmic radiation, vacuum, and time, what would they see? Imagine yourself immersed in a sea of starlight that spreads out over 1,000,000 light-years in every direction. The stars are not clustered tightly as they might be in a typical galactic core. Instead, they are dispersed, flowing outward in a gentle gradient, as if an unseen hand had stirred the heart of the galaxy, loosening the gravitational glue that normally binds such a structure tightly together. It's not just that A2261 BCG lacks a black hole, it's that it wears the signature of its absence like a scar, plainly visible in the structure of its diffuse, evacuated core. This emptiness tells a story, a cosmic narrative written in the language of stellar dynamics, light profiles, and gravitational equilibrium. In a normal, elliptical galaxy, the core is shaped by billions of years of gravitational interactions, by the slow dance of stars orbiting an all-consuming mass. The stars in the core lose energy through complex processes and migrate inward, where they are either captured by the central black hole or contribute to the steep rise in brightness typically observed in these regions. But A2261 BCG defies that norm. Its core has a shallow light profile, what astronomers call a core cusp discrepancy. Rather than peaking sharply at the center, the brightness plateaus, forming a flat, sprawling luminosity distribution. This plateau is indicative of a so-called core scouring event, often theorized to occur when two supermassive black holes interact gravitationally during a merger. In such a scenario, as the black holes spiral toward each other, they sling nearby stars outward through three-body interactions, effectively flinging them away and hollowing out the galactic center. This process can enlarge the core, producing the flat brightness profile seen in A2261 BCG. But here's the catch. This process alone doesn't remove the black hole. It merely reshapes the star population. For the black hole to actually disappear, either being expelled entirely or recoiling off-center, something more extreme must happen. A black hole merger followed by a recoil from asymmetrical gravitational wave emission could do it, but such events are believed to be extraordinarily rare, requiring precise asymmetries in mass, spin, and alignment. Still, when theory and observation collide, and a galaxy like A2261 BCG reveals itself with no central black hole in sight, astronomers must take seriously the possibility that such an unlikely scenario has, in fact, occurred. Simulations of galactic mergers have been instrumental in supporting this possibility. Using advanced supercomputers, researchers modeled the collision of two galaxies, each with its own central black hole. Over millions of years of simulated time, these black holes lose orbital energy, draw closer, and finally merge. When they do, they produce a burst of gravitational waves. If the emission of these waves is directional, more intense in one direction than the other, the resulting merged black hole can be launched in the opposite direction, like a cannonball fired from a gravitational slingshot. Depending on the kick velocity and the galaxy's escape velocity, the black hole might either settle into a new orbit offset from the core or be flung out of the galaxy entirely. In the case of A2261 BCG, the latter seems to be the more consistent explanation. The massive core and lack of concentrated light in the center suggest a high-energy event that not only scoured the stellar population, but removed the gravitational anchor entirely. Yet this raises another question: where is the ejected black hole now? A black hole of such scale, presumably billions of solar masses, should leave a trail. It should carry with it a small entourage of stars, gas, and dust, gravitationally bound to it as it hurtled through space. These trailing stars, often referred to as a hypercompact stellar system, could be observable with the right instruments. They would appear as a fast-moving, compact cluster of stars emitting X-rays or infrared radiation. Yet despite deep observations, such a cluster has not been conclusively identified near A2261 BCG. Several stellar clumps in the vicinity have drawn attention as candidates, but none have displayed the definitive signatures of an active or dormant black hole. Could the black hole be dormant? That's certainly possible. Black holes do not always accrete matter, and when they don't, they are practically invisible. An ejected black hole traveling through intergalactic space with no fuel to feed on would emit little to no radiation. It would be a ghost, undetectable unless it happened to pass through a dense cloud of gas or lens the light of a background object. This possibility makes the search all the more difficult and the mystery all the more tantalizing. A massive, invisible black hole, ejected from its parent galaxy and lost to the void, would be an unprecedented discovery. A solitary wanderer adrift in the cosmic sea. This concept of a rogue black hole is both thrilling and haunting. The universe, already dark and vast beyond comprehension, may be host to untold numbers of black holes that have been expelled from their homes. These are not the stellar mass black holes that form from collapsing stars. These are giants, ancient, supermassive entities that once sat at the heart of galaxies, now cast adrift. If a 2261 BCG's black hole is one such rogue, then its study offers a rare window into this hidden population. The implications go far beyond this single galaxy. If supermassive black hole ejections are more common than we think, then our understanding of galaxy formation and evolution must be re-examined. How many galaxies have had their cores reshaped or hollowed out by such events? How many supermassive black holes are lurking in intergalactic space, invisible to our eyes and instruments? And how do these processes affect the overall dynamics of galaxy clusters? The very presence of a 2261 BCG in the Abell 2261 cluster complicates the narrative further. Galaxy clusters are gravitationally bound conglomerates of galaxies, gas, and dark matter. They are the largest structures in the universe held together by gravity. The central galaxy in such a cluster typically plays a dominant role in the cluster's dynamics. Its black hole, in particular, is believed to regulate cooling flows in the intracluster medium through a process known as active galactic nucleus (AGN) feedback. Without a central black hole to inject energy into the surrounding gas, a cooling catastrophe could ensue, leading to an overproduction of stars and dramatic changes in the cluster's evolution. So far, a 2261 BCG doesn't show such an overproduction, suggesting either that the black hole was ejected recently, or that another mechanism is at work regulating star formation in the cluster's core. Meanwhile, the cluster's own gravitational center may be slightly offset from a 2261 BCG, another possible indication of recent disruption. If the galaxy has undergone a powerful merger and lost its black hole, the gravitational balance of the cluster might have shifted slightly, leading to observable asymmetries in the distribution of galaxies and hot gas. Future observations with next-generation instruments, such as the James Webb Space Telescope and the Vera C. Rubin Observatory, may shed more light on these subtle clues, revealing whether a 2261 BCG is an outlier, or a harbinger of a deeper cosmic truth. For now, the mystery remains unsolved. Astronomers continue to search, theorize, and wonder. The question of a 2261 BCG's missing black hole is not merely a footnote in galactic evolution. It is a challenge to our understanding of the cosmos. It is a reminder that for all our technological prowess, for all our elegant theories and detailed simulations, the universe still holds surprises that defy expectation. Sometimes, the greatest discoveries are not found in what we see, but in what we don't. A 2261 BCG, in its silent enormity, tells a story louder than most galactic narratives ever could. Its very structure seems to whisper across time, something happened here, something extraordinary, powerful, and rare. Its core isn't just large, it's the largest ever observed, spanning a mind-bending 10,000 light-years across. That's more than 3 times the size of a typical core in a galaxy of similar type and mass. This alone makes it an object of fascination. But size is only part of the mystery. The real enigma lies in what's not at the center, the absent gravitational monarch, the invisible force that should be reigning over the billions of stars, a supermassive black hole. In most giant elliptical galaxies, a central black hole weighing millions or even billions of solar masses is standard fare. These cosmic beasts influence their host galaxies far beyond their event horizons, shaping star formation, regulating gas flows, and anchoring the core with gravity so immense that time itself stretches near them. Yet a 2261 BCG lacks all evidence of such a presence. No high-velocity stars circling an unseen center. No energetic jets shooting across space. No X-ray emissions betraying the infall of matter. This silence is deafening in astrophysical terms. Scientists have scoured the central region of a 2261 BCG with instruments like the Hubble Space Telescope and the Chandra X-ray Observatory, seeking any trace of a black hole's fingerprints. They expected to find either radiation from an accretion disk if the black hole were active, or telltale stellar dynamics if it were dormant but massive. Neither has surfaced. Instead, there is only a strange emptiness, as though the galactic throne sits unoccupied. Some stars in the core region move unusually slowly, which further contradicts expectations. If a massive black hole were present, it would whip stars around at high velocities, an unmistakable sign of deep gravitational influence. But in A2261 BCG, the stars appear to drift almost aimlessly, relaxed, unperturbed. This velocity dispersion, or rather the lack of it, strengthens the hypothesis that the central black hole may be entirely missing, not just quiet. This has led scientists to consider one of the most dramatic theories in galactic evolution, that A2261 BCG's central black hole was ejected during a galactic merger. When galaxies collide, their central black holes, initially orbiting separately, sink toward the center of the new merged galaxy due to dynamical friction, gravitational interactions that rob them of orbital energy. Over time, the two black holes draw close enough to form a binary system, eventually spiraling together until they merge in a cataclysmic event. This merger releases gravitational waves, ripples in the fabric of spacetime that carry away enormous energy. However, if the gravitational waves emitted during the merger are not symmetric in all directions, because of differences in the black hole's spin, mass, or alignment, the resulting force can push the newly formed black hole away from the center. This gravitational wave recoil can launch the merged black hole at incredible velocities, potentially exceeding several thousand kilometers per second. If the kick velocity exceeds the escape velocity of the host galaxy's core, the black hole is effectively flung out, banished from its domain. This is the scenario that might have played out in A2261 BCG. If so, the supermassive black hole would now be a wanderer, perhaps still within the galaxy's outer reaches, or maybe traveling alone through the intergalactic wilderness of the Abell 2261 cluster. One of the potential smoking guns of this theory is the presence of off-center stellar clumps. These are dense pockets of stars near the core but not at the very center, possible remnants of the stars that were gravitationally bound to the black hole when it was ejected. A few such clumps have been identified in A2261 BCG. They are intriguing, not just because they exist, but because they might be following a path consistent with having been tugged by a massive object, an invisible one. Astronomers have conducted spectroscopic analyses of these clumps, hoping to detect abnormal motions or velocity dispersions that would indicate the presence of a black hole hiding among them. A compact stellar system with unusually high internal velocities might be the remnant signature of the ejected black hole's gravitational influence. So far, the results are inconclusive. Some data suggest slightly elevated velocity dispersions, but nothing definitive. The search continues, with even more sensitive instruments planned for future observations. This leads to a broader question: how common are such events in the cosmos? If gravitational wave recoil is responsible for A2261 BCG's black hole loss, could other galaxies have suffered similar fates? If so, the implications are massive. It would mean that rogue black holes, unbound from any galaxy, may be more numerous than we realize. These are not merely cosmic oddities. There would be a hidden population of enormous mass and power, dark travelers scattered across the vast gulfs between galaxies. The difficulty in detecting them lies in their invisibility. Without a supply of gas to accrete, they do not emit radiation. They become gravitational ghosts. Only by their gravitational effects, through lensing, for instance, or through disturbances in stellar motion, can they be inferred. But such effects are subtle, and require immense precision to observe. In the cold emptiness of intergalactic space, a rogue supermassive black hole could pass silently for eons, leaving no trace. It is here that A2261 BCG becomes more than just a curiosity. It becomes a symbol of the unknown, the unobserved, the untamed aspects of the universe that our theories are only beginning to touch. This galaxy is a cosmic laboratory, presenting an anomaly that forces astronomers to test the limits of their models. Does every massive galaxy harbor a black hole? A 2261 BCG says maybe not. Our gravitational wave kicks strong enough to eject a billion solar mass black hole? A 2261 BCG replies, perhaps they are. It's not just the missing black hole that fascinates. It's the questions it raises about galactic structure, dark matter distribution, feedback mechanisms, and even cosmic evolution as a whole. If a galaxy can survive, structurally and dynamically, without its central black hole, then perhaps these entities, though powerful, are not as essential as once thought. Or perhaps the survival is temporary. Perhaps the absence will eventually cause instabilities that lead to the galaxy's slow unraveling. We don't know. Not yet. Meanwhile, the Abell 2261 cluster continues its silent rotation. A 2261 BCG remains in its midst, silent, enigmatic, and stately. Its halo of stars shines softly in the darkness, their motions unhurried, their orbits gentle. There's no sign of the fierce gravitational whip a central black hole would create. No bursts of energy, no flaring jets of X-rays, no violent feasting upon infalling matter. Just calm. Vast, unnatural calm. And so, astronomers return to their data. They refine their models, reprocess their images, run simulations over millions of computational hours. They turn their eyes toward the next generation instruments, waiting for them to come online. Perhaps one day a new survey will spot a compact cluster of stars moving too fast. Perhaps gravitational lensing will betray the invisible hand of a massive object passing in front of a distant quasar. Perhaps the smoking gun will finally be revealed. Or perhaps the mystery will deepen, as cosmic mysteries often do. A 2261 BCG's puzzle is not merely an astrophysical anomaly. It challenges the very paradigms on which our understanding of galaxies is built. For decades, the cosmic rulebook has emphasized the central role of supermassive black holes in galaxy formation and regulation. These behemoths were thought to form hand-in-hand with their host galaxies, growing through mergers and accretion in a tightly coupled evolutionary dance. Yet the apparent absence of a black hole at the heart of a 2261 BCG implies that either this dance can be disrupted, or that the rulebook itself is incomplete. The galaxy's characteristics, while spectacular on their own, make even less sense without a central black hole. A 2261 BCG's luminosity is among the highest in its cluster, and its stellar population indicates it is ancient and evolved. Typically, such galaxies display a cuspy core, with star density increasing steeply toward the center due to the gravitational well of the black hole. Instead, a 2261 BCG shows a flat core, almost evacuated of stars, a structure known as a core-scoured galaxy. This phenomenon can be explained by a binary black hole system having flung stars outward during its death spiral. But if the black hole has since been ejected, that would leave behind precisely what we see, a wide, smooth, and diffuse central region devoid of the expected gravitational signature. This hypothetical ejection isn't just a whimsical thought. Computer simulations have demonstrated that gravitational wave recoil is not only possible but probable under the right conditions. These simulations show that the new, merged black hole can receive a recoil kick of several thousand kilometers per second depending on asymmetries in the gravitational wave emission. Such a force is staggering, equivalent to accelerating something with the mass of several billion suns fast enough to escape even the deep gravitational pull of a giant galaxy. But detecting the aftermath of such an ejection is notoriously difficult. That's why the case of a 2261 BCG is so captivating. It may be the cleanest observational evidence we have of this event ever occurring. If confirmed, it would provide a unique window into both general relativity and galaxy evolution on a cosmological scale. Researchers have tried to model the distribution of stars in a 2261 BCG's core, looking for inconsistencies that could only be explained by a missing black hole. The challenge lies in the data. Much of what we know comes from imaging and spectroscopy conducted by the Hubble Space Telescope and other observatories with limited resolution relative to the vast distances involved. The galaxy is more than 3 billion light-years away. At that distance, even a massive object like a black hole becomes a whisper in the noise of background radiation and foreground interference. Adding another layer of complexity is the environment in which a 2261 BCG exists, the Abell 2261 galaxy cluster. Galaxy clusters are dynamic environments, full of gravitational interactions, mergers, gas flows, and dark matter halos. It's possible that a 2261 BCG has interacted with nearby galaxies or subclusters in a way that altered its structure or even contributed to the black hole's ejection. It may also be that tidal forces, acting over millions of years, have reshaped its core in ways we don't yet fully understand. Yet among the possibilities, the gravitational recoil scenario remains the most consistent with what is observed. If the galaxy once hosted a binary black hole system that merged and then recoiled, what became of the expelled black hole? Where is it now? Could we find it? Astronomers have proposed looking for signs of compact star clusters moving unusually fast, detached from the main body of the galaxy. These so-called hypercompact stellar systems would be the entourage of stars that remained gravitationally bound to the black hole after the kick. They would move as a unit, gliding through intergalactic space like a stellar lifeboat dragged by an invisible captain. Observing such a system would be an extraordinary feat, as it would offer a direct way to see a runaway black hole through its gravitational influence alone. Even more ambitiously, researchers suggest hunting for the trail left by the black hole's departure. When a supermassive black hole is ejected, it may leave behind ripples in the density of stars, or even shockwaves in surrounding gas. In a galaxy as massive as a 2261 BCG, those effects could persist for hundreds of millions of years. Searching for these patterns requires high-resolution imaging and data processing techniques capable of separating the subtlest signals from noise. Future telescopes may provide the tools we need to detect these signatures. The James Webb Space Telescope, with its infrared capabilities and unmatched resolution, could observe the heart of a 2261 BCG with new eyes. Additionally, the upcoming Nancy Grace Roman Space Telescope, and next-generation ground-based observatories like the Extremely Large Telescope, ELT, may have the sensitivity and precision to find faint objects moving through the darkness. These instruments might one day confirm the presence of a rogue black hole or detect the dynamical relics of its passage. But even without direct confirmation, the implications of a 2261 BCG's black hole mystery extend far. If gravitational wave recoil is powerful enough to remove black holes from galaxies, it means that supermassive black holes may not be as stable or permanent as once thought. That, in turn, has profound effects on our understanding of how galaxies evolve. For one, the lack of a central black hole would disrupt feedback mechanisms that regulate star formation. Black holes, particularly when active, emit vast amounts of energy in the form of jets and radiation, which heat up surrounding gas and prevent it from collapsing into new stars. This process, known as AGN feedback, plays a crucial role in galaxy quenching, halting star formation in massive galaxies. Without a black hole to regulate this process, a galaxy might form stars unchecked until its gas supply runs dry. But a 2261 BCG is an old galaxy, composed mostly of aging, red stars with little active star formation, suggesting that either a black hole was once present and removed only recently, or another mechanism is performing a similar regulatory role. Moreover, the discovery raises the possibility of other galaxies with similarly missing black holes. If a 2261 BCG is not unique, then our surveys of black hole populations could be missing a substantial number of objects that are simply not where we expect them to be. This would skew our models of cosmic mass distribution, black hole formation rates, and even the expected signals from gravitational wave detectors. And there's a poetic dimension too, an existential one. Imagine a supermassive black hole, ejected from its home, dragging along a shroud of stars, exiled into the cosmic sea with no way to return. It becomes a nomad, a lost king without a throne, journeying through the void in silence. These rogue entities may be the most mysterious travelers in the universe, and a 2261 BCG might just be the first clue to their presence. The universe is not static. It is restless. Things change, collide, merge, disappear. A 2261 BCG stands as a testament to this cosmic impermanence. Its sheer size and the calmness of its core tell a story not of peace, but of a violent past whose echoes still shape its present. The galaxy may have devoured others. It may have birthed and banished a monster. And now, it sits in the stillness of aftermath, waiting to be understood. Astronomers continue to probe, to simulate, to wonder. The mystery remains unsolved, but not unpursued. Perhaps one day, a faint dot on a deep sky image will move in an unexpected way, and we'll know, the black hole was never destroyed. It was merely set free. The idea that a supermassive black hole, one with a mass of billions of suns, could be exiled from its galactic throne is, by all measures, a cosmic twist that defies conventional expectations. In the story of A2261 BCG, this twist becomes central to an unfolding drama on a scale nearly unimaginable. But to truly appreciate its significance, we must examine every layer of this mystery with meticulous care. The astrophysical environment of A2261 BCG, the observable clues left behind, the simulations that support the ejection hypothesis, the broader implications for galactic evolution, and even the philosophical underpinnings that arise from contemplating such a scenario, all are threads in a vast and intricate tapestry. First, let us dwell longer on the structural enigma of A2261 BCG. The central core of this galaxy measures about 10,000 light-years across, 4 times larger than the next biggest known galactic core and an astonishing 20 times wider than the average elliptical galaxy core. This alone is a massive anomaly. The inner structure of such a galaxy should be more compressed, held together by the gravitational influence of a central mass. Its light profile should steepen dramatically toward the center, reflecting the increased density of stars pulled inward by a dominant gravitational well. But instead, the light curve of A2261 BCG flattens conspicuously in the core, suggesting that something immense was removed from the heart of this galaxy. That something is assumed to be the supermassive black hole that once anchored the galaxy. The concept of gravitational wave recall presents a compelling theoretical explanation for its absence. When two black holes spiral together and merge, their interaction emits gravitational waves, ripples in the fabric of space-time. If this emission is asymmetric, it can impart momentum to the resulting black hole, effectively giving it a kick. The strength of that kick depends on the mass ratio of the merging black holes, their spins, and the angles at which they collide. Calculations show that such a kick can, in extreme cases, reach speeds exceeding 4,000 km per second. To put that into context, the escape velocity from a massive elliptical galaxy like A2261 BCG is typically under 2,000 km per second. This means that under the right, or wrong conditions, a black hole could be launched clear out of its galaxy, never to return. If A2261 BCG underwent such an event, we would expect it to leave behind certain telltale signatures. The expanded core fits this narrative. During the inspiral of two supermassive black holes, their gravitational tug would scatter stars away from the center, creating a depleted core. After the final merger, the gravitational kick would remove the remnant black hole, leaving no central object to attract new stars inward. Over cosmic timescales, that core would remain puffy and sparse, as the dynamical equilibrium could never be restored. Yet even this explanation raises new questions. How recently did this ejection occur? How long can the galaxy remain in this state before other processes begin to reform its core? Could a new black hole begin forming through gas accretion or the collapse of massive stars in the central region? If so, how long would that take, and would it leave a different observational footprint than the original? To help answer such questions, astronomers use n-body simulations, highly detailed computer models that simulate the gravitational interactions between millions or billions of stars, gas particles, and dark matter components. These simulations have confirmed that black hole recoil can produce the kind of large, flat core structure seen in A2261 BCG. Moreover, they show that such a structure can persist for hundreds of millions of years, perhaps even longer, depending on the density of the surrounding stellar population and the dynamical history of the galaxy. In the case of A2261 BCG, which resides in the densely packed Abell 2261 cluster, gravitational interactions with neighboring galaxies may have prolonged or reinforced the core's unusual shape. Interestingly, this galaxy's core does contain 4 bright knots of light, compact stellar groupings that orbit near its center. Some researchers have speculated that one of these knots could be the remnant of the missing black hole's entourage. If the black hole retained a small cluster of stars bound to its gravity during ejection, this collection could still be detectable as a hypercompact stellar system. But identifying which of these knots, if any, houses the rogue black hole requires ultra-precise measurements of stellar velocities and motions, something current telescopes can only barely achieve at that distance. Spectroscopic studies may offer another clue. By examining the light emitted by these stellar knots in the central region, astronomers can look for velocity shifts or broadened spectral lines that indicate rapid motion, either of the stars themselves or of ionized gas moving under the influence of a massive, unseen object. If a rogue black hole is present in one of these knots, its gravity could be causing stars to whip around at immense speeds, creating measurable Doppler effects in the light we observe. And yet, as of now, no definitive evidence has emerged. Every search has come up inconclusive, reinforcing the sense that the central black hole is truly gone. But this only intensifies the allure of the mystery. Could the black hole have recoiled so fast and so far that it's now drifting through intergalactic space, virtually undetectable except through indirect gravitational effects? If so, how many other rogue black holes might exist out there, silent, wandering relics of ancient cosmic violence? This scenario leads to larger implications that reach well beyond a single galaxy. If gravitational wave recoil is common, then it implies a non-trivial population of unbound black holes in the universe. These black holes may no longer be visible through traditional means, such as X-ray emissions or active galactic nuclei, but they would still bend light and warp space through their immense gravity. Future gravitational wave observatories, such as LISA, the Laser Interferometer Space Antenna, may be able to detect the signature of these wandering giants directly. Additionally, the existence of galaxies without central black holes disrupts the coevolution theory. It implies that a galaxy can remain relatively stable, at least for a time, even without the central engine that supposedly governs its growth and behavior. It also raises the possibility that feedback mechanisms other than black holes may be capable of regulating star formation, such as stellar winds, supernova explosions, or the heating effects of cosmic rays. A 2261 BCG becomes a crucial test case for these alternate models. This galaxy also invites deeper questions about the role of dark matter in maintaining galactic cohesion. Without a central black hole, something must still be providing enough gravitational binding to prevent the core from completely dispersing. Dark matter halos are the most likely candidates, and studying a 2261 BCG could provide insight into the distribution and behavior of dark matter in massive elliptical galaxies. Even the philosophical implications are profound. In a universe governed by entropy and ruled by decay, black holes have always represented something eternal, something final, the ultimate endpoints of mass and time. They are the silent judges of the cosmos, swallowing matter and light with equal indifference. But the idea that a black hole could itself be uprooted, thrown from its home like a cosmic fugitive, challenges that sense of permanence. It reminds us that even the most titanic forces in the universe are subject to chaos and change. In many ways, a 2261 BCG acts like a mirror. It reflects our current limits of understanding. It shows us the boundaries of what our instruments can detect and what our theories can explain. But it also acts like a doorway, a glimpse into realms of astrophysics we are only beginning to explore. Every pixel of its diffuse core, every ripple in its stellar population, every unseen motion in its orbiting knots, each is a whisper from a universe more complex and more dynamic than we dared to imagine. And so astronomers will keep watching. New instruments will aim their eyes at the galaxy's core. New data will be collected, analyzed, reanalyzed, and debated. Theories will be tested, refined, rejected, and reborn. Because the story of a 2261 BCG is not finished. It is still being written, in the skies above and in the minds of those who look up and wonder. But as we continue to probe deeper into the enigma that is A2261 BCG, the mystery only seems to expand, not resolve. What we are confronting is not merely the absence of a single astronomical object, it is the unraveling of assumptions that have guided astrophysical thought for decades. In the traditional narrative of galaxy formation and evolution, supermassive black holes serve as both the seeds and the anchors of their host galaxies. They are born from the collapse of early, massive stars or dense regions in the young universe and grow through mergers and accretion. Over billions of years, they become the gravitational heart of their galaxies, exerting influence on everything from star formation to gas dynamics to the motion of entire stellar populations. But if a galaxy like A2261 BCG can exist without such a core anchor, what does that imply for the thousands, perhaps millions, of other massive galaxies scattered throughout the cosmos? Is A2261 BCG a freak exception, the product of an improbable cosmic accident? Or is it the tip of an iceberg, a signal that our understanding of galactic evolution is more incomplete than we ever thought? To begin unraveling this, astronomers have turned not just to telescopes but to algorithms. Machine learning and artificial intelligence are being employed to scour through massive datasets, catalogs of galaxy shapes, cores, and light profiles, in search of other galaxies that share similar structural anomalies. By using pattern recognition and unsupervised classification techniques, researchers aim to find hidden analogs of A2261 BCG, galaxies that, while not identical, might show signs of similarly evacuated cores or abnormal stellar dynamics. The early results are mixed. Some candidates do exist, but none yet match the dramatic characteristics of A2261 BCG. Its central void remains unusually large, its symmetry oddly perfect, and its missing black hole shockingly absent. This rarity lends even more urgency to understanding its history. Consider the timescales involved. Galactic mergers, the type capable of producing a central black hole collision and recoil, happen over spans of hundreds of millions of years. The ejection event itself, if it occurred, would have been cataclysmic yet sudden on cosmic timescales. In just a moment, perhaps a few minutes or hours, a gravitational wave recoil could send a supermassive black hole hurtling into space. What remains is the aftermath, a slow rebalancing of gravitational dynamics that takes eons to unfold. In this context, A2261 BCG may be caught in the aftermath, frozen in a moment of imbalance. The galaxy's light profile, its soft-edged core, and the peculiar distribution of stars all suggest a structure that has not yet fully recovered from a traumatic event. It is as though we are observing a scar, one left not on flesh, but on the very fabric of space. And this metaphor of a cosmic scar invites another line of investigation. What happens to a galaxy psychologically, if one can borrow such anthropomorphic language, after its black hole is removed? The center of the galaxy no longer serves as a gravitational anchor. Stars that would have migrated inward remain in suspension. Gas that might have formed new stars now drifts unperturbed. The feedback loop that normally operates, where the black hole heats and ejects gas to regulate star formation, is broken. And yet A2261 BCG is still a galaxy. It still holds together. It still shines. This resilience, this capacity for structure in the absence of order, is both scientifically fascinating and symbolically profound. As researchers explore this, they also examine the knots of stars within the central region. These knots, compact star clusters, are not unusual in themselves. Many galaxies have nuclear star clusters, globular clusters, and other small, dense groupings of stars. But in A2261 BCG, these knots are not arranged randomly. They are positioned near the very center, in locations that suggest they may be co-orbiting or reacting to a common gravitational disturbance. This has led to the provocative hypothesis that one of these knots might actually contain the exiled black hole itself. If this is true, it presents an extraordinary opportunity, the chance to directly study a supermassive black hole that has been dislodged from its galactic core but still carries with it a small entourage of bound stars. This hypothetical object is known in theoretical literature as a Hypercompact stellar system, or HCSS. An HCSS is expected to be very small, perhaps a few dozen light-years across, but incredibly dense, with internal stellar motions governed by the black hole's gravity. The detection of such an object would not only confirm the recoil hypothesis but also open a new chapter in observational astrophysics. But detecting an HCSS is not easy. At the distance of A2261 BCG, roughly 2.7 billion light-years from Earth, spatial resolution becomes a limiting factor. Even the Hubble Space Telescope, with its fine-tuned optics, struggles to resolve such tight structures at that range. Upcoming instruments like the James Webb Space Telescope, with its infrared sensitivity and larger aperture, may offer new hope. Likewise, the extremely large telescope, ELT, under construction in Chile, with its 39-meter primary mirror, will revolutionize high-resolution imaging in the next decade. With these tools, astronomers may finally peer into the heart of one of these knots and determine whether a black hole still lurks there. Meanwhile, the theoretical groundwork continues to evolve. Recent studies have expanded the possible outcomes of black hole mergers, showing that not only can recoil kicks vary dramatically in velocity, but they can also affect the spin, accretion dynamics, and event horizon properties of the resulting black hole. These effects feed into models of galaxy evolution, informing everything from AGN feedback models to the growth rate of black holes across cosmic epochs. In some scenarios, the absence of a central black hole can even allow a galaxy to enter a quasi-stable state with prolonged star formation, a kind of second wind in its evolutionary life. A 2261 BCG might be in such a transitional state. Without a black hole to quench star formation, its central regions may slowly reignite, forming new generations of stars over millions of years. Alternatively, the lack of gravitational cohesion might cause these regions to remain dormant, suspended in a state of stellar stasis. Observations of the galaxy's color, metallicity gradients, and stellar populations could help unravel this possibility. If younger, bluer stars are detected in the core, it would suggest ongoing or recent star formation. If older, redder stars dominate, it would support the idea of a long-term quiescent core. What also makes a 2261 BCG fascinating is its cosmic context. It is not an isolated galaxy, it is the brightest cluster galaxy, BCG, of the Abell 2261 cluster, a massive grouping of hundreds of galaxies bound together by gravity. BCGs are typically the oldest and most massive galaxies in any cluster. They sit at the gravitational center, often surrounded by a halo of hot gas, dark matter, and satellite galaxies. In this environment, gravitational interactions are constant. Tidal stripping, mergers, and accretion events are common. For a black hole to be ejected in such a crowded neighborhood, and to remain undetected, suggests an exceptional set of circumstances. It raises the question, could the missing black hole now reside in another galaxy within the cluster? If its velocity vector was not perfectly aligned with open space, it could have passed close to another galaxy, potentially becoming gravitationally captured. This leads to the speculative but tantalizing possibility that some smaller galaxy within Abell 2261 now houses a supermassive black hole far larger than it should possess. Finding such a mismatch, where a galaxy's mass and its central black hole are wildly disproportionate, would offer indirect confirmation of this narrative. Astrophysicists are now examining the cluster with this possibility in mind. They search for galaxies whose velocity dispersion, X-ray emissions, or central brightness suggest a gravitational anomaly. They analyze weak lensing data to look for warps and distortions that could indicate an unseen mass. And they run simulations of cluster dynamics, inserting a rogue black hole and watching its path as it weaves through the gravitational landscape of Abell 2261. These simulations are time-consuming and complex, but they offer one of the few ways to test the plausibility of this hypothesis. And as this investigative web expands outward, from a single galaxy to its cluster, from light curves to gravitational waves, the mystery of A2261 BCG becomes more than just a singular puzzle. It becomes a cosmic story about movement, transformation, and consequence. A story about how even the most stable structures in the universe can be disrupted. A story about how events that occurred billions of years ago can leave traces still visible today. And a story about how the universe, in all its vastness, never ceases to surprise us. The implications of a galaxy like A2261 BCG missing its central black hole ripple far beyond its immediate surroundings. For decades, supermassive black holes have been considered essential engines powering some of the most energetic phenomena in the universe. Active galactic nuclei, quasars, and relativistic jets all owe their existence to matter accreting onto these cosmic giants. Their gravitational influence shapes the formation of stars, regulates galactic gas, and sculpts the evolution of galaxies from early times to the present day. The discovery, or in this case, the conspicuous absence, of such a central black hole challenges these paradigms. To understand why, it's important to appreciate the scale and nature of supermassive black holes. Unlike stellar black holes, which form from the remnants of massive stars and typically measure only a few to tens of solar masses, supermassive black holes tip the scales at millions to billions of times the mass of our Sun. Their formation remains an active area of research, but prevailing theories suggest they grow through hierarchical mergers and accretion of matter, gradually feeding and expanding over billions of years. Positioned at the centers of galaxies, they create deep gravitational wells that trap stars, gas, and even light, profoundly influencing the architecture and life cycle of their host systems. In most galaxies, the presence of a supermassive black hole is unmistakable. Their signature comes not only from direct emissions, like X-rays or radio jets, but also from indirect observations such as the motion of stars in their vicinity. The stellar velocities near a galactic center often reveal a dark, massive object exerting tremendous gravitational force. The correlation between the mass of a galaxy's central black hole and its bulge properties, known as the M-sigma relation, has been a cornerstone of astrophysical models. Yet, A2261 BCG breaks this mold. Despite its enormous size and mass, it lacks the expected signs of a supermassive black hole. This raises profound questions. Has the black hole been ejected, or was it never there in the first place? If ejected, what cosmic event was powerful enough to dislodge an object weighing billions of solar masses? If never present, what does that mean for our understanding of galaxy formation? One promising explanation involves the concept of gravitational wave recoil. When two supermassive black holes spiral together and merge, a cataclysmic event releasing enormous energy in the form of gravitational waves, the resulting merged black hole can receive a kick. This recoil happens because the gravitational waves carry away linear momentum asymmetrically, propelling the black hole at speeds that can reach thousands of kilometers per second. In some cases, this velocity is sufficient to eject the black hole from the galactic core entirely. Such a black hole recoil event would dramatically reshape its host galaxy. The sudden absence of the black hole's gravitational anchor leads to a diffuse and unusually large core, consistent with observations of A2261 BCG. Yet, detecting the black hole after its ejection is challenging. It may still lurk within the galaxy as a hypercompact stellar system or even travel through intergalactic space, invisible and silent. Understanding this phenomenon demands the integration of multi-wavelength observations and sophisticated simulations. Optical data reveal the distribution of stars and the galaxy's structure, while X-ray observations track hot gas possibly influenced by the black hole's presence or absence. Radio telescopes probe for jets or emissions that might betray a wandering black hole. Meanwhile, gravitational wave observatories like LIGO and Virgo, and in the future LISA, provide direct evidence of black hole mergers, helping us piece together the frequency and impact of these violent events. Moreover, the case of A2261 BCG pushes us to rethink feedback mechanisms in galaxy evolution. Normally, active black holes regulate star formation by heating and expelling gas, a process critical to preventing runaway growth. Without this regulation, galaxies might undergo prolonged periods of star formation or evolve along unexpected paths. Observing A2261 BCG star populations and gas dynamics can thus reveal how galaxies behave when their central black holes vanish. In addition to the scientific insights, A2261 BCG serves as a powerful reminder of the universe's complexity and our evolving understanding of cosmic structures. It highlights the limits of current theories and the importance of continued exploration with ever more advanced technology. Future telescopes, from the James Webb Space Telescope to the Extremely Large Telescope, promise to shed light on these mysteries with unprecedented clarity. As we look ahead, the story of A2261 BCG intertwines with broader questions about black hole physics, galaxy formation, and cosmic history. It invites us to explore the nature of gravity, the fabric of spacetime, and the violent events that shape the universe on grand scales. Each new discovery related to this enigmatic galaxy brings us closer to comprehending the delicate balance between order and chaos that governs the cosmos. This journey is far from over. With every observation, every simulation, and every theoretical breakthrough, we move toward unraveling the secrets of A2261 BCG. In doing so, we not only decode the fate of a single galaxy but also deepen our understanding of the universe itself, a universe filled with wonders still waiting to be discovered. The mystery of A2261 BCG's missing central black hole invites us to delve deeper into the very processes that govern the cosmos on the largest scales. To truly grasp the significance of this anomaly, it is important to reflect on the context in which this galaxy exists, and the key astrophysical mechanisms thought to shape such colossal structures. Located approximately 3 billion light-years away, A2261 BCG sits at the center of the galaxy cluster Abell 2261. Galaxy clusters themselves are among the universe's largest gravitationally bound systems, containing hundreds or thousands of galaxies, massive amounts of hot gas-emitting X-rays, and dark matter halos that dominate their overall mass. The central galaxies in these clusters, brightest cluster galaxies (BCGs), are typically massive elliptical galaxies with extremely large stellar populations and, almost invariably, supermassive black holes at their cores. A2261 BCG stands out because of its extraordinary size and a uniquely diffuse core, which is much larger and more fluffy than typical galactic centers. Normally, galaxies with massive black holes show steeply rising brightness profiles toward their centers, as stars are tightly packed in the deep gravitational well created by the black hole's pull. Yet, in A2261 BCG, the core is unusually flat and extended, suggesting the gravitational grip expected from a supermassive black hole is missing or at least significantly diminished. The absence of a central black hole in such a massive galaxy contradicts a fundamental assumption in modern astrophysics: the coevolution of galaxies and their central black holes. This concept asserts that galaxies and their supermassive black holes grow together in a symbiotic relationship. Feedback from black holes regulates star formation, shapes galactic morphology, and influences the chemical evolution of the interstellar medium. Without a central black hole, these feedback processes are disrupted, potentially altering the evolutionary trajectory of the galaxy. One of the most fascinating hypotheses explaining this absence involves the violent merger of two supermassive black holes. When galaxies collide, their black holes spiral inward, emitting gravitational waves in the process. These waves can carry away momentum asymmetrically, resulting in a recoil kick that propels the merged black hole away from the galactic center. The magnitude of this kick depends on several factors, including the masses, spins, and orientations of the merging black holes. If the kick velocity exceeds the escape velocity of the host galaxy's core, the black hole can be ejected entirely, wandering through intergalactic space. Alternatively, it may oscillate around the galaxy's core for millions or billions of years, causing the galaxy's central structure to become disturbed or expanded. The large, diffuse core observed in A2261 BCG fits well with simulations of such a scenario, lending strong support to the gravitational wave recoil hypothesis. Detecting the ejected black hole itself, however, presents significant challenges. Without the accretion of matter to produce bright emissions, a supermassive black hole can remain virtually invisible. Astronomers have sought potential signatures such as hypercompact stellar systems, small clusters of stars bound tightly around the rogue black hole, or offset X-ray sources that might betray its location. So far, these searches have yet to yield conclusive evidence, leaving the black hole's whereabouts an open question. The technological and methodological advancements in astrophysics play a crucial role in exploring these phenomena. The Hubble Space Telescope's detailed imaging was critical in identifying the unusual core of A2261 BCG. Meanwhile, X-ray observatories such as Chandra have helped characterize the hot gas environment around the galaxy, offering clues about the galaxy's mass distribution and dynamic state. Future instruments with enhanced resolution and sensitivity will be vital for probing deeper into this mystery. Furthermore, gravitational wave astronomy is on the verge of revolutionizing our understanding of black hole mergers. While current ground-based detectors like LIGO are sensitive primarily to mergers of stellar mass black holes, planned space-based observatories such as LISA, Laser Interferometer Space Antenna, will be able to detect gravitational waves from supermassive black hole collisions across the universe. Observations from these missions may directly observe recoil events, confirming or refuting the ejection hypothesis. A 2261 BCG's enigmatic core also encourages theoretical work in galaxy formation and evolution. Modeling the effects of black hole ejection on stellar dynamics, gas inflows, and star formation requires complex simulations that incorporate gravity, hydrodynamics, and feedback processes. These simulations help predict observational signatures that astronomers can seek, bridging theory and data. This case forces astrophysicists to reconsider the resilience of galactic centers. How stable are these cores without their gravitational anchor? Can galaxies sustain themselves and evolve normally if their central black holes vanish? What does this mean for the population statistics of black holes and the demographics of galaxies? Each question opens a new frontier of inquiry. Beyond the scientific curiosity, A2261 BCG serves as a profound reminder of the universe's capacity to surprise and challenge. The cosmos continually defies our expectations, pushing the boundaries of knowledge and prompting ever more ingenious investigations. As we unravel the mysteries of this giant galaxy and its missing black hole, we also deepen our connection to the vast, dynamic universe we inhabit. Ultimately, the story of A2261 BCG is more than an astrophysical puzzle. It is an epic tale of cosmic forces, violent events, and the intricate dance of matter and gravity on an unimaginable scale. It embodies the spirit of discovery that drives astronomy and the quest to understand the fundamental workings of the universe. The enigma of A2261 BCG's missing central black hole invites us to re-examine the fundamental mechanisms that govern galaxy formation and evolution. It pushes us to rethink the gravitational dynamics at play within the densest cosmic environments, and to question the permanence of what we often assume to be the universe's most stable and dominant structures. One cannot discuss A2261 BCG without reflecting on the nature of brightest cluster galaxies themselves. BCGs reside at the gravitational heart of galaxy clusters, environments teeming with interactions, collisions, and mergers. These colossal galaxies typically form through the cannibalization of smaller galaxies, accumulating stars and dark matter over billions of years. This process, known as hierarchical merging, inevitably leads to the growth of a supermassive black hole, as the cores of merging galaxies coalesce and their central black holes spiral inward due to dynamical friction. However, A2261 BCG defies this script. Its core, instead of displaying the dense, cusp-like stellar distribution expected near a supermassive black hole, reveals a broad, shallow brightness profile. This observation strongly suggests a disruption or absence of the central black hole's gravitational influence. To unravel this, researchers employ sophisticated simulations of galaxy mergers, which demonstrate that when two supermassive black holes collide and merge, the emission of gravitational waves can produce a recoil velocity sufficient to dislodge the newly merged black hole from the galactic center. This recoil effect is not merely a theoretical curiosity. It arises from the asymmetrical emission of gravitational waves during the final stages of black hole mergers. The magnitude and direction of the recoil depend sensitively on the mass ratio of the merging black holes, their spin magnitudes, and orientations. Under certain configurations, the merged black hole can receive a kick exceeding several thousand kilometers per second, enough to escape even the deep gravitational potential wells of massive galaxies like A2261 BCG. If the central black hole was ejected, it would leave behind a galaxy core depleted of stars near the center, a core scoured by the gravitational interactions of the binary black hole before merger and further expanded by the absence of the black hole's gravitational pull. This scenario aligns with the observed characteristics of A2261 BCG's core, making it a prime candidate for hosting a recoiling black hole. Detecting the actual ejected black hole remains a formidable challenge. Without accreting material, such a black hole emits no light and can be nearly invisible across the electromagnetic spectrum. However, theoretical models predict that a recoiling black hole may carry a cluster of tightly bound stars, forming a hypercompact stellar system. These stars, gravitationally bound to the black hole, could serve as luminous tracers of the rogue black hole's location. Searches using high-resolution imaging have yet to identify such a system in A2261 BCG's vicinity, but the search continues. Beyond the observational efforts, the implications of a missing black hole extend to the broader understanding of galactic ecosystems. Supermassive black holes regulate star formation through feedback processes, where energy and momentum from accretion-driven outflows heat and expel gas, preventing excessive star formation that would otherwise consume the galaxy's gas reservoir rapidly. Without this feedback, a galaxy might experience unchecked star formation or accumulate gas in ways that alter its morphology and evolutionary path. Additionally, the absence of a black hole raises questions about the relationship between black holes and dark matter halos. The growth of supermassive black holes is intertwined with the gravitational potential of dark matter, which dominates the mass budget of galaxies and clusters. The ejection of a central black hole could disrupt this delicate interplay, affecting the dynamics of the surrounding dark matter and baryonic components. Furthermore, the case of A2261 BCG invites us to consider the frequency of such black hole ejection events across cosmic time. How common are these events, and what role do they play in shaping the population of supermassive black holes and galaxies? The answers to these questions have profound implications for models of galaxy formation and the assembly of large-scale structure in the universe. Gravitational wave astronomy offers a promising avenue to answer these questions. The detection of gravitational waves from supermassive black hole mergers by future space-based observatories like LISA will provide direct insights into the rates, masses, and spins of merging black holes. Observing the recoil signatures in these waves will confirm the mechanisms that can eject black holes from galactic centers, transforming our understanding of galaxy black hole coevolution. Moreover, the multi-messenger approach combining electromagnetic observations and gravitational wave data promises a holistic view of these violent cosmic events. Identifying electromagnetic counterparts to gravitational wave sources will allow astronomers to track the aftermath of mergers, including potential black hole recoil and ejection. The story of A2261 BCG also reflects the dynamic and evolving nature of astrophysical knowledge. It demonstrates how unexpected observations challenge prevailing theories, prompting the development of new models and the deployment of cutting-edge observational tools. This cycle of discovery, questioning, and refinement is at the heart of scientific progress. As technology advances, with next-generation telescopes like the James Webb Space Telescope and the Extremely Large Telescope, astronomers will probe galaxies like A2261 BCG with unprecedented clarity. These instruments will reveal the detailed structure of galaxy cores, search for faint hypercompact stellar systems, and characterize the distribution of gas and dark matter. Combined with increasingly sensitive gravitational wave detectors, they will unravel the fate of missing black holes and the role they play in the cosmic tapestry. In contemplating the mysteries of A2261 BCG, we are reminded that the universe is not a static backdrop but a vibrant arena of continual change, shaped by forces both seen and unseen. The absence of a central black hole in such a massive galaxy is a profound testament to the complexity and dynamism of cosmic evolution, inviting us to explore deeper and think broader about the forces that shape the cosmos. The journey into understanding A2261 BCG's missing central black hole also opens a window onto the broader cosmological context in which galaxies evolve. Galaxy clusters, like the one housing A2261 BCG, are among the largest gravitationally bound structures in the universe, containing hundreds or thousands of galaxies, vast quantities of hot intracluster gas, and enormous amounts of dark matter. The interactions and mergers within these clusters serve as laboratories for studying the extreme physics that govern the universe. A 2261 BCG sits at the core of the Abell 2261 galaxy cluster, which is located roughly 3 billion light-years away from Earth. The cluster's mass and gravitational pull influence the motion and fate of its constituent galaxies and the supermassive black holes at their centers. The environment within such clusters is incredibly dynamic. Galaxies often collide or pass close by each other, their mutual gravities tugging and twisting structures, triggering bursts of star formation, or stripping gas and stars from galactic disks. In these turbulent conditions, supermassive black holes, cosmic heavyweights millions to billions of times the mass of the Sun, play pivotal roles. They anchor their host galaxies, influence star formation through their powerful feedback mechanisms, and are thought to drive the evolution of galaxies from star-forming spirals to massive ellipticals. Their mass correlates with the mass and velocity dispersion of their host galaxies' bulge, an empirical relationship known as the M-sigma relation, which hints at a deep physical connection between galaxies and their central black holes. Yet A2261 BCG defies this paradigm. Its extraordinarily large and diffuse core appears to lack the expected gravitational grip of a supermassive black hole. This is not only unusual but may signify a rare stage in galaxy evolution or an extreme outcome of galactic collisions. Detailed observations using the Hubble Space Telescope have revealed that the core of A2261 BCG is one of the largest ever observed, spanning thousands of light-years, much larger than typical galaxy cores. The low stellar density at the center contrasts sharply with the compact, bright cores seen in other giant ellipticals, further fueling the mystery. Instead of a steep spike in brightness at the core, indicative of stars tightly bound by a massive central black hole's gravity, the light profile is flat or even hollowed out. This morphology suggests that powerful gravitational interactions may have ejected the central black hole or significantly disturbed the core. Numerical simulations show that when two supermassive black holes merge, the newly formed black hole can receive a gravitational wave recoil, or kick, that might push it out of the galaxy's center. Such an event would leave behind a core depleted of stars and gas. The kick velocity can be enormous, sometimes surpassing the escape velocity of the host galaxy, depending on the black hole's spins and orbital configurations before merging. If the black hole escapes, it would carry with it only a small cluster of tightly bound stars, potentially creating a wandering, hyper-compact stellar system moving through the cluster. Searching for this rogue black hole and its accompanying stellar cluster is challenging. They would be faint, compact, and difficult to distinguish from other small star clusters in the cluster environment. However, astronomers have used a combination of X-ray, radio, and optical observations to look for signs of accretion activity or unusual stellar motions that might betray the black hole's presence. If found, such a wandering supermassive black hole would have profound implications. It would confirm the violent nature of black hole mergers and the potential for black holes to be displaced from their galactic centers. This would revise our understanding of galaxy black hole coevolution, the growth of supermassive black holes, and the dynamics of dense galaxy clusters. The absence of a central black hole in A2261 BCG also challenges models of active galactic nuclei, AGN, where accretion onto supermassive black holes powers enormous energy output, influencing the surrounding gas and star formation. Without a central black hole, the galaxy's evolution might proceed differently, potentially altering its star formation history, morphology, and interaction with the intracluster medium. Moreover, this case raises questions about the fate of ejected black holes. Do they wander indefinitely through intergalactic space, or can they be recaptured by other galaxies or clusters? What observable signatures might they produce? Could rogue black holes be common, yet hidden, components of the cosmic landscape? These questions intertwine with fundamental aspects of astrophysics and cosmology, including the growth of structure in the universe, the distribution of dark matter, and the physics of gravitational waves. The detection of gravitational waves by observatories like LIGO has already revolutionized astrophysics by confirming the existence of stellar mass black hole mergers. Future space-based detectors, such as LISA, will extend this to supermassive black hole mergers, enabling direct study of the phenomena that could create systems like A2261 BCG. Studying A2261 BCG and its missing black hole thus provides a crucial testbed for theories of gravity, galaxy formation, and black hole physics. It embodies the frontier of observational astronomy and theoretical astrophysics, where surprises from the cosmos drive scientific discovery forward. As astronomers continue to refine their observations and simulations, the mystery of A2261 BCG challenges us to rethink assumptions and explore new paradigms. This colossal galaxy, quietly harboring an invisible absence at its heart, stands as a monument to the complexity and wonder of the universe. Beyond the immediate mystery of A2261 BCG's missing black hole lies an even deeper layer of cosmic intrigue. How such an enormous galaxy could form and evolve without the gravitational anchor that typically governs its core. Understanding this requires delving into the intricate processes of galaxy formation, mergers, and the role of supermassive black holes in shaping the architecture of the cosmos. Galaxies do not form in isolation. They are the product of billions of years of cosmic evolution, governed by the interplay of dark matter, gas dynamics, star formation, and black hole growth. Large galaxies like A2261 BCG are often the result of multiple merger events, where smaller galaxies collide and coalesce under gravity, their stars, gas, and central black holes combining to form a larger, more massive galaxy. These mergers are chaotic and transformative. The gravitational forces reshape stellar orbits, funnel gas toward the center, and trigger intense episodes of star formation. At the core, the central black holes of the merging galaxies spiral inward, losing energy through dynamical friction until they form a binary system. Over time, the binary shrinks as it radiates gravitational waves, ultimately merging into a single, more massive black hole. This process, while understood in theory, can have dramatic consequences. The merged black hole can receive a recoil kick from anisotropic emission of gravitational waves, causing it to oscillate around or even escape the galactic center. If this kick is strong enough, as hypothesized for A2261 BCG, the black hole may be displaced or ejected, leaving behind a core lacking the typical supermassive black hole's gravitational influence. The stellar core's unusual size and light distribution in A2261 BCG supports this scenario. Instead of stars tightly packed around a black hole, the core appears scoured, with a low density of stars, possibly due to stars being flung out by the gravitational slingshot effect during the black hole's final end spiral. This process carves out a hollow in the stellar distribution, consistent with observations. Understanding these extreme events requires cutting-edge simulations that incorporate general relativity, hydrodynamics, and stellar dynamics. These simulations have revealed that the recoil velocities can reach thousands of kilometers per second, sufficient to eject black holes from even massive galaxies. Although such high-velocity kicks are rare and depend sensitively on the black hole's spin orientations and masses. If A2261 BCG's black hole was ejected, what is its current fate? One possibility is that it now wanders through the intergalactic medium of the Abell 2261 cluster. This rogue supermassive black hole would be nearly invisible except for potential signs of accreting gas or interactions with surrounding matter. Detecting such a black hole requires deep, high-resolution surveys across multiple wavelengths: X-ray to detect hot gas emissions, radio to catch jets or synchrotron radiation, and optical to identify a hypercompact cluster of stars bound to the black hole. The potential discovery of such a wandering black hole would be revolutionary. It would confirm predictions of gravitational wave recoil and provide direct evidence for the dynamical processes shaping galaxy cores. Moreover, it could illuminate the pathways of black hole growth and feedback, including how some black holes might be lost from galaxies, altering the coevolution of black holes and their hosts. In addition to these dynamical processes, the environment of the Abell 2261 cluster contributes to A2261 BCG's evolution. Clusters contain hot intra-cluster gas-emitting X-rays, pervasive dark matter halos, and a population of galaxies undergoing interactions. Ram pressure stripping, tidal forces, and the cluster's gravitational potential will all influence the gas supply and star formation in member galaxies. Interestingly, A2261 BCG's lack of a central black hole could also affect how it interacts with this environment. Supermassive black holes often regulate star formation through energetic feedback. Jets and winds from the black hole's accretion disk heat surrounding gas, preventing it from cooling and forming stars. Without such a central engine, A2261 BCG might experience different star formation rates or gas dynamics compared to typical brightest cluster galaxies. This divergence could have consequences for the galaxy's color, morphology, and future growth. Over cosmic timescales, these factors influence the mass distribution, chemical enrichment, and stellar population of the galaxy, potentially making A2261 BCG a unique laboratory for studying galaxy evolution under unusual conditions. Furthermore, the implications of a missing black hole extend to cosmological scales. Black holes contribute to the growth of large-scale structure by influencing the distribution of matter and energy through feedback mechanisms. They also serve as markers of cosmic history, tracing the buildup of galaxies and clusters across billions of years. The case of A2261 BCG challenges astronomers to reconsider assumptions about the universality of black hole-galaxy correlations. It raises fundamental questions. Are there other massive galaxies without central black holes? How common are recoiling or ejected supermassive black holes? What are the long-term impacts on galaxy formation and cluster dynamics? Answering these questions will require advances in observational technology and theoretical modeling. Future instruments like the James Webb Space Telescope, extremely large telescopes, and next-generation X-ray observatories will probe the detailed structure of galaxy cores and search for faint signatures of wandering black holes. Simultaneously, improvements in computational astrophysics will enable more precise simulations of black hole mergers, recoil dynamics, and galaxy cluster interactions. Combining these approaches will help build a comprehensive picture of phenomena like those observed in A2261 BCG. As we explore this cosmic enigma, A2261 BCG stands as a testament to the universe's complexity and the ongoing quest to understand the forces shaping galaxies and black holes. It reminds us that even the largest, most massive structures can harbor secrets that challenge established paradigms and inspire new discoveries. The story of A2261 BCG is far from complete. Each observation and simulation adds a piece to the puzzle, revealing the dynamic interplay of gravity, black holes, stars, and cosmic evolution. It highlights the profound connections linking the tiniest scales of quantum gravity and black hole mergers to the grandest scales of galaxy clusters. In the coming decades, continued research into A2261 BCG and similar systems promises to uncover deeper truths about the universe's workings. This giant galaxy with its mysteriously missing central black hole offers a unique window into the cosmic ballet of matter, energy, and gravity, inviting us to look ever deeper into the heart of the cosmos. The enigma of A2261 BCG's missing central black hole pushes astronomers to reconsider the intricate feedback loops that connect supermassive black holes to their host galaxies. It has long been understood that these black holes play a crucial role in regulating star formation within galaxies through what is called active galactic nucleus (AGN) feedback. When material falls into the black hole's accretion disk, enormous amounts of energy are released, often driving powerful jets and winds that can either heat up or expel the surrounding gas. This feedback is vital for preventing runaway star formation, which could otherwise consume a galaxy's gas reservoir prematurely. In the absence of a central black hole, as possibly exemplified by a 2261 BCG, this regulatory mechanism may be severely altered. The lack of AGN feedback could lead to an atypical cooling of the galaxy's gas, potentially fueling prolonged star formation episodes or causing gas to accumulate without being expelled or heated. This might explain certain unusual properties observed in a 2261 BCG's core and extended halo, such as its diffuse stellar distribution and peculiar gas dynamics. Moreover, the gravitational influence of a supermassive black hole shapes the orbits of stars near the galactic center. Without it, stars in a 2261 BCG's core exhibit different kinematic behaviors, potentially forming a more isotropic, less tightly bound structure. This is consistent with observations of the galaxy's unusually large and flat stellar core, a feature rarely seen in other giant elliptical galaxies. To fully grasp the implications, astronomers are employing integral field spectroscopy and high-resolution imaging across multiple wavelengths. These observations allow them to map stellar velocities and populations in fine detail, revealing clues about the galaxy's formation history and current state. The data suggests that a 2261 BCG may have undergone a series of major mergers over billions of years, during which its central black hole was either ejected or displaced, disrupting the usual formation of a dense, cuspy stellar core. Another fascinating dimension to this mystery is the potential presence of a recoiling black hole traveling through the galaxy, or the larger cluster environment. Such a black hole might carry with it a small cluster of bound stars, forming what is called a hypercompact stellar system, HCSS. Detecting these HCSSs is an observational challenge, as they are compact, faint, and easily lost amidst the bright background of cluster galaxies. However, the identification of such systems would provide direct evidence for gravitational wave recoil and offer invaluable insights into black hole merger physics. In addition to observational pursuits, theoretical astrophysicists simulate scenarios of black hole mergers with varying spin configurations and mass ratios to predict recoil velocities and ejection probabilities. These simulations have demonstrated that under specific conditions, black holes can be expelled at speeds exceeding 1,000 km per second, enough to escape even the deep gravitational wells of giant galaxies or clusters. If a 2261 BCG's black hole was indeed ejected, this event would also affect the galaxy cluster's overall dynamics. Black holes contribute to the cluster's gravitational potential and energy budget, influencing gas heating and cooling on cluster-wide scales. The absence of one or more supermassive black holes could alter these processes, affecting the intracluster medium's temperature and density, with ripple effects on galaxy evolution throughout the cluster. Furthermore, a 2261 BCG provides an important case study for understanding the fate of supermassive black holes in dense cosmic environments. Clusters like Abell 2261 are bustling hubs of galactic interactions, where frequent mergers and close encounters occur. This dynamical environment may enhance the chances of black hole ejection or displacement, making such systems prime targets for studying black hole demographics and merger histories. The broader context includes the role of gravitational waves, the ripples in spacetime generated by massive accelerating objects like merging black holes. The detection of gravitational waves by observatories such as LIGO and Virgo has revolutionized astrophysics, confirming predictions from general relativity and opening a new observational window onto the universe. Systems like a 2261 BCG connect these groundbreaking discoveries to galaxy evolution, linking microphysical phenomena to macroscopic cosmic structures. In the future, the planned Laser Interferometer Space Antenna (LISA) mission will detect gravitational waves at lower frequencies, capable of observing supermassive black hole mergers directly. This will provide crucial data on merger rates, recoil velocities, and black hole growth over cosmic time, enhancing our understanding of galaxies like a 2261 BCG and their missing black holes. As investigations continue, new instruments and techniques will refine our picture of a 2261 BCG's core, searching for signs of a displaced black hole or constraining its properties if truly absent. Such work requires coordinated efforts across astronomy, astrophysics, and gravitational physics, exemplifying the interdisciplinary nature of modern cosmic research. Ultimately, A2261 BCG stands as a profound cosmic mystery, one that challenges established models and invites us to explore the delicate dance of gravity, matter, and energy on the grandest scales. It reminds us that the universe is not static but a dynamic arena where even the most massive and seemingly immutable objects can undergo extraordinary transformations. The story of this giant galaxy, its unusually large and diffuse core, and its mysteriously missing central black hole continues to unfold, promising to deepen our understanding of the cosmos and the fundamental forces that shape it. The question of where A2261 BCG's central black hole might be, or whether it is truly absent, leads to a fascinating examination of observational techniques used to detect such objects. Traditionally, astronomers identify supermassive black holes by their gravitational influence on nearby stars and gas, or by the high-energy emissions produced when matter accretes onto them. This can include X-ray emissions, radio jets, or bright optical/UV signatures known as active galactic nuclei, AGN. In the case of A2261 BCG, despite extensive searches using the Hubble Space Telescope, the Chandra X-ray Observatory, and ground-based spectroscopic observations, there is a striking absence of such telltale signs. The core of the galaxy, while enormous and diffuse, lacks the bright, compact emission one would expect from an actively accreting black hole. This absence is puzzling because galaxies of this mass almost invariably host black holes millions or billions of times the mass of our Sun. The size of A2261 BCG's core itself is extraordinary. It is one of the largest known galaxy cores, spanning over 3,000 light-years. This is vastly larger than typical elliptical galaxies, which generally exhibit more concentrated stellar cores or cusps. Theories about core formation include the scouring effect of binary black holes. When two supermassive black holes merge, their gravitational interactions can eject stars from the central region, carving out a low-density core. In A2261 BCG, the sheer size of the core suggests that some powerful dynamical event occurred, possibly involving multiple mergers or the ejection of a black hole, which would have a profound impact on the central stellar distribution. One hypothesis is that during a merger of two galaxies, each harboring its own supermassive black hole, the resulting binary black hole eventually coalesced and produced a gravitational wave recoil strong enough to eject the newly merged black hole from the center of A2261 BCG. The speed of this recoil can reach thousands of kilometers per second, sufficient to escape the galaxy's gravitational grip. This would leave behind a galaxy core bereft of its central black hole, consistent with what is observed. Alternatively, the black hole may not have been fully ejected but rather displaced to an off-center location within the galaxy. If the black hole is wandering, it may be detectable through the motion of stars or by observing compact, off-nuclear X-ray sources. Researchers have looked for such indicators but so far without conclusive evidence. The mystery deepens when considering the consequences of a missing black hole on the galaxy's future. Without a central black hole, processes such as the regulation of star formation and the heating of surrounding gas may be disrupted. This could lead to atypical star formation rates or gas dynamics compared to other galaxies of similar size and type. It may also affect the long-term structural evolution of the galaxy. The environment of A2261 BCG within the Abell 2261 galaxy cluster also offers insights. Clusters are crowded places where galaxies frequently interact, merge, and influence each other gravitationally. These dynamic conditions may increase the likelihood of black hole ejections, as gravitational interactions between multiple massive bodies become more common. Thus, A2261 BCG may represent a natural laboratory for studying the end stages of black hole mergers and the impact on galaxy evolution. Understanding the nature of A2261 BCG's missing black hole also ties into broader cosmological questions. The growth and evolution of supermassive black holes are linked to the formation of galaxies themselves. By studying extreme cases like this galaxy, astronomers can refine models of galaxy assembly, merger histories, and the role of feedback processes. As technology advances, future observations using next-generation telescopes, such as the James Webb Space Telescope, JWST, and the Extremely Large Telescope, ELT, will provide unprecedented resolution and sensitivity. These instruments may detect subtle features indicative of a hidden or displaced black hole or reveal new aspects of the galaxy's core structure and stellar populations. In parallel, advancements in gravitational wave astronomy will complement electromagnetic observations by directly detecting the mergers of supermassive black holes. This synergy promises to unlock a deeper understanding of black hole physics and galaxy evolution, especially in systems like A2261 BCG that challenge current paradigms. Thus, the giant galaxy A2261 BCG and its mysteriously missing central black hole remain at the frontier of astrophysical research. Its study not only challenges existing theories but also propels the development of new ones, expanding our knowledge of the universe's most massive and enigmatic structures. The prospect of detecting a recoiling or wandering black hole within A2261 BCG has driven astronomers to explore innovative observational strategies. One such approach involves searching for hypercompact stellar systems, HCSS, which are tightly bound clusters of stars that may accompany an ejected supermassive black hole. These systems form because stars gravitationally bound to the black hole are carried along during its recoil, resulting in a small, dense stellar cluster moving through space. Identifying an HCSS requires deep, high-resolution imaging combined with detailed spectroscopic analysis to distinguish such a system from typical globular clusters or background galaxies. HCSS candidates are expected to exhibit unique kinematics and spectral signatures, including unusual velocity dispersions and potentially signs of accretion if the black hole is still feeding on nearby matter. Detecting such systems within or near A2261 BCG would provide compelling evidence for the ejection hypothesis and offer a rare glimpse into the aftermath of supermassive black hole mergers. Moreover, the presence or absence of a central black hole in A2261 BCG has significant implications for dark matter distribution models and massive galaxies. The central gravitational potential shaped by a supermassive black hole influences how dark matter halos respond and evolve. Without this central mass concentration, the dark matter profile in the galaxy's core could differ substantially, affecting predictions of gravitational lensing, galaxy rotation curves, and the behavior of satellite galaxies. The case of A2261 BCG also invites questions about the population statistics of galaxies with missing or displaced black holes. Are such phenomena common but difficult to detect, or are they truly rare cosmic events? Large-scale surveys of galaxy cores combined with multi-wavelength observations will be crucial in addressing this question. By building a census of galaxies with unusual core properties or absent AGN signatures, astronomers can better understand the frequency and conditions that lead to black hole ejections. Furthermore, studying the stellar populations within A2261 BCG's core provides clues to its evolutionary timeline. Spectroscopic data reveal the ages, metallicities, and motion of stars, indicating periods of intense star formation or quiescence. The stellar population's distribution can reflect past mergers, accretion events, and dynamical disturbances linked to black hole activity or ejection. Such detailed stellar archaeology helps reconstruct the galaxy's history, complementing direct black hole searches. At a fundamental level, the missing black hole in A2261 BCG challenges the assumption that every massive galaxy hosts a central supermassive black hole. This assumption underpins many models of galaxy formation and cosmological simulations. Revising it could affect our understanding of galaxy scaling relations, black hole mass functions, and the coevolution of galaxies and their central black holes. The mystery of A2261 BCG also intersects with studies of gravitational wave recoil, a phenomenon predicted by Einstein's theory of general relativity. The detection of gravitational waves from merging stellar mass black holes by LIGO and Virgo has confirmed aspects of this theory, but supermassive black hole mergers remain out of reach for current detectors. Future missions like LISA will target these massive mergers, potentially validating recoil velocities capable of ejecting black holes from galactic centers. A 2261 BCG stands as a tantalizing astrophysical laboratory where such theoretical predictions might be observed indirectly. In sum, the story of a 2261 BCG's giant, diffuse core and the elusive central black hole is a compelling saga at the crossroads of observational astronomy, theoretical physics, and cosmology. It highlights the dynamic and sometimes violent processes shaping the universe's largest structures. Each discovery and hypothesis tested around this galaxy deepens our appreciation for the complexity and wonder of cosmic evolution. Exploring the dynamics within a 2261 BCG's vast core, astronomers have observed that the stellar velocities there are unusually low for a galaxy of its size. Normally, the gravitational pull of a supermassive black hole creates steep velocity gradients near the center, as stars orbit rapidly in response to the black hole's immense mass. However, in a 2261 BCG, stars move more sluggishly, which aligns with the hypothesis that the central black hole may be missing or displaced. This atypical stellar motion suggests a fundamentally different gravitational environment. The absence of a dominant central mass means that the galaxy's inner gravitational potential is smoother and less steep. This has implications not just for stellar orbits, but also for the stability of the galaxy's core and the mechanisms of star formation within it. Without the strong tidal forces a black hole generates, gas clouds may evolve differently, potentially allowing star formation to proceed under altered conditions. Further insights come from detailed simulations modeling the gravitational interactions of merging black holes and the resulting gravitational wave recoil effects. These simulations show that when two supermassive black holes merge, the asymmetric emission of gravitational waves can impart a kick to the resultant black hole, propelling it out of the galactic center at speeds sometimes exceeding 5,000 km per second. This kick depends on several factors: the masses of the merging black holes, their spin orientations, and the eccentricity of their orbit before merging. Such kicks could explain why a 2261 BCG appears to have an enormous core with no central black hole. The gravitational recoil would eject the merged black hole, leaving behind a stellar core that has been scoured by prior interactions but now lacks the supermassive object expected at its heart. This scenario is consistent with the galaxy's diffuse core and the absence of a detectable active nucleus. However, detecting a recoiling black hole directly remains challenging. Such an object might still be embedded within the galaxy but displaced from its center, or it might have been ejected entirely into intergalactic space. If the black hole carries with it a cluster of stars or a mini accretion disk, it could produce unique observational signatures, but these would be faint and easily missed without targeted high-resolution surveys. Additionally, the role of the intracluster environment must be considered. A 2261 BCG resides within the Abell 2261 galaxy cluster, a massive structure containing hundreds of galaxies bound together by gravity and pervaded by hot intracluster gas-emitting X-rays. Interactions within such a cluster, tidal forces, galaxy harassment, and multiple merger events can greatly influence the structure and evolution of member galaxies, including their central black holes. Cluster dynamics could enhance the probability of black hole ejection events. Close encounters between galaxies may trigger mergers and thus black hole coalescence, while the cluster's deep gravitational potential might affect whether ejected black holes escape entirely or remain bound in the cluster outskirts. This broader context is critical to understanding not only a 2261 BCG's unique properties, but also the population statistics of supermassive black holes in dense environments. On a theoretical level, the existence of a galaxy like a 2261 BCG with a missing or displaced supermassive black hole challenges models that posit a near-universal black hole galaxy coevolution. If black holes can be ejected and remain absent for extended periods, this affects how we interpret scaling relations such as the m-sigma relation, which links black hole mass to the velocity dispersion of stars in the galactic bulge. These relations have been cornerstone tools in understanding galaxy formation and evolution. The missing black hole also raises questions about the feedback mechanisms that regulate star formation and gas dynamics in galaxies. Active supermassive black holes influence their host galaxies by injecting energy into the surrounding medium, preventing runaway cooling and excessive star formation. Without such feedback, galaxies might experience unusual evolutionary paths, possibly producing more extended or diffuse stellar distributions, as seen in A2261 BCG. As our observational capabilities improve, new facilities like the James Webb Space Telescope and extremely large ground-based observatories will provide sharper images and deeper spectra, revealing finer details of A2261 BCG's core and potentially uncovering the fate of its missing black hole. These instruments could detect faint accretion signatures, displaced nuclear activity, or subtle stellar dynamical signatures pointing to a recoiling or wandering black hole. The story of A2261 BCG continues to inspire research not only into galaxy cores and black holes but also into fundamental physics, such as gravitational wave emission and the behavior of matter under extreme gravitational fields. It sits at the nexus of astrophysics, cosmology, and relativity, embodying the mystery still to be unraveled in our understanding of the universe. The profound mystery of A2261 BCG's missing central black hole continues to ripple through multiple facets of astrophysics, prompting researchers to rethink long-standing assumptions about galaxy evolution and black hole demographics. One important aspect to consider is the galaxy's formation history, which may hold crucial clues to its present-day peculiarities. Unlike typical giant elliptical galaxies with steep central brightness peaks, A2261 BCG's core is unusually flat and extended, a feature known as a core deficit. This suggests a violent past involving repeated mergers and energetic interactions. In the hierarchical model of galaxy formation, large elliptical galaxies like A2261 BCG grow through a series of mergers of smaller galaxies. Each merger event brings its own central black hole, setting the stage for binary black hole formation and eventual coalescence. The gravitational slingshot effect of merging black holes can eject stars from the core, carving out the large, diffuse region observed. However, this process typically leaves behind a merged supermassive black hole at the center. The absence of such a black hole in A2261 BCG is therefore an extraordinary anomaly. Simulations of multiple black hole mergers reveal complex dynamics, including scenarios where gravitational wave recoil might remove the black hole entirely. These models also suggest that if the black hole is ejected with high velocity, it could carry with it a retinue of tightly bound stars, forming a hypercompact stellar system that might be detectable far from the galaxy's core. Identifying such a cluster would provide compelling evidence for the black hole's fate and offer a new window into post-merger black hole dynamics. The implications of A2261 BCG's missing black hole extend to our understanding of active galactic nuclei, AGN, and their role in galaxy ecosystems. Supermassive black holes powering AGN inject vast amounts of energy into their surroundings through jets and radiation, regulating star formation and heating interstellar gas. Without a central black hole, A2261 BCG might lack this regulatory mechanism, potentially leading to unusual star formation histories or altered gas dynamics within the galaxy. Moreover, the absence of a central black hole challenges the empirical scaling relations widely used to estimate black hole masses, such as the m-sigma relation, which correlates black hole mass with the velocity dispersion of stars in the galaxy's bulge. A 2261 BCG's deviation from these relations suggests that such correlations may have exceptions or that additional parameters influence black hole galaxy coevolution. The search for the missing black hole also intersects with efforts to detect gravitational waves from supermassive black hole mergers. While current ground-based detectors like LIGO and Virgo are sensitive to stellar mass black hole mergers, future space-based observatories such as LISA, Laser Interferometer Space Antenna, will target the low-frequency gravitational waves emitted by supermassive black holes. Observations of galaxies like A2261 BCG provide empirical targets and motivation for these missions, linking electromagnetic observations to gravitational wave astronomy. A further layer of complexity arises from the role of the galaxy cluster environment. A 2261 BCG is the brightest galaxy in the Abell 2261 cluster, residing in a dense environment where interactions among cluster members are frequent. These interactions can strip gas, alter galaxy trajectories, and trigger mergers, affecting the growth and behavior of central black holes. The cluster's gravitational potential may also influence whether a recoiling black hole escapes the galaxy entirely or remains bound within the cluster halo. In addition, studies of the hot intracluster medium via X-ray observations reveal the energetic interplay between galaxies and their environment. The absence of central AGN activity in A2261 BCG might affect the heating and cooling cycles of intracluster gas, influencing star formation rates and the distribution of matter within the cluster. The mystery of A2261 BCG's missing central black hole exemplifies the intricate dance of cosmic forces shaping galaxy evolution. It highlights the need for multi-wavelength observations, combining optical, radio, X-ray, and gravitational wave data to fully unravel the galaxy's secrets. Each new discovery around this enigmatic galaxy enriches our broader understanding of the universe's grand design. As technology advances and new observatories come online, the story of A2261 BCG promises to remain a focal point of astrophysical research. It challenges us to refine our models, question established paradigms, and explore the frontiers of cosmic knowledge, reminding us that the universe still holds profound mysteries waiting to be uncovered. The enigmatic absence of a central black hole in A2261 BCG also invites speculation about alternative processes that might mimic or obscure such an object's presence. One such possibility involves the presence of an intermediate mass black hole, or a system of smaller black holes distributed within the core, instead of a single, supermassive entity. This distribution could create gravitational effects that differ from those expected around a solitary, dominant black hole, potentially explaining the observed stellar motions and core structure. These smaller black holes could be remnants from previous galaxy mergers or the result of disrupted black hole binaries that never fully coalesced. The dynamics within such a system would be complex, with interactions between multiple black holes affecting star orbits and gas accretion patterns. Detecting these subtle influences requires extremely sensitive instruments capable of resolving fine-scale movements and emissions within the galaxy's core. Another avenue of research considers the role of dark matter in the central regions of A2261 BCG. Although dark matter is generally thought to dominate the outer halos of galaxies, its distribution in the innermost parts remains uncertain. If dark matter forms a dense core or cusp within A2261 BCG, it might contribute significantly to the gravitational potential in ways previously underestimated. This could influence the overall mass profile and the motions of stars near the center, potentially masking or compensating for the absence of a supermassive black hole. On the observational front, the challenges of detecting a central black hole, or its absence, are significant. Traditional methods rely on observing high-velocity stellar motions or emissions from accreting gas in the X-ray and radio wavelengths. However, if the black hole is dormant, obscured by dust, or displaced from the galactic center, these signals may be weak or absent. This necessitates the use of innovative techniques, such as adaptive optics, integral field spectroscopy, and deep radio interferometry, to probe the heart of A2261 BCG with unprecedented detail. The puzzle deepens when considering the timescales involved. If the black hole was ejected relatively recently, its influence on the stellar distribution and gas dynamics would still be evident. Conversely, if the ejection occurred billions of years ago, the galaxy may have had time to relax and adapt to the absence, complicating efforts to trace back the event. Understanding these temporal aspects is crucial for reconstructing the galaxy's evolutionary narrative. From a cosmological perspective, A2261 BCG serves as a natural laboratory for studying the interplay between black holes, galaxies, and their environments on the largest scales. The galaxy's location within a massive cluster means it experiences frequent interactions and accretion events, which can dramatically reshape its structure and black hole population. Insights gained here may apply broadly to other massive galaxies and clusters across the universe. The implications for galaxy feedback mechanisms are profound. Without a central black hole to regulate gas cooling and star formation, a 2261 BCG might display atypical patterns of starburst activity or gas accretion. Studying these processes could reveal new modes of galaxy growth and evolution, expanding our understanding of how galaxies develop in diverse environments. Furthermore, the potential discovery of a recoiling or wandering black hole would open a new chapter in black hole astrophysics. Tracking such an object as it moves through the galaxy or cluster would provide direct evidence of gravitational wave recoil effects and offer opportunities to study black hole dynamics outside traditional galactic nuclei. As astronomers continue to probe a 2261 BCG with cutting-edge instruments, each new observation contributes a piece to the intricate puzzle of its missing black hole. This ongoing investigation not only challenges existing theories but also drives the development of new models that incorporate the complex physics of black hole mergers, gravitational waves, and galaxy cluster dynamics. Ultimately, the story of a 2261 BCG underscores the dynamic and ever-evolving nature of the cosmos. It reminds us that even the most massive and seemingly well-understood structures can harbor profound mysteries, pushing the boundaries of human knowledge and inspiring the quest to unravel the secrets of our universe. Beyond the immediate astrophysical implications, the mystery surrounding a 2261 BCG invites a philosophical reflection on our place in the universe and the nature of scientific inquiry itself. The search for the missing black hole embodies the spirit of curiosity that drives astronomy, the desire to understand phenomena that defy expectations and challenge prevailing paradigms. This quest exemplifies how each answer in science often leads to new questions, propelling us into deeper and more nuanced investigations. Considering the observational techniques employed to study a 2261 BCG, the advancements in telescope technology and data analysis methods have been pivotal. Space-based observatories like the Hubble Space Telescope have provided high-resolution imaging essential for mapping the galaxy's diffuse core and detecting subtle features indicative of past merger events. Meanwhile, ground-based facilities equipped with adaptive optics have enabled the resolution of stellar motions near the core, refining estimates of mass distributions and potential black hole influence. The role of multi-wavelength astronomy cannot be overstated. X-ray observations from satellites such as Chandra have been crucial in searching for energetic signatures typical of accreting black holes. The absence of strong X-ray emissions from the core region of a 2261 BCG adds weight to the hypothesis that its central black hole is either missing, dormant, or displaced. Radio observations similarly complement this picture by probing jet activity and synchrotron emissions often associated with active galactic nuclei. From a theoretical standpoint, numerical simulations modeling galaxy mergers and black hole dynamics provide valuable frameworks to interpret the data. These simulations incorporate general relativity, hydrodynamics, and stellar dynamics to predict how merging black holes interact with their surroundings and the likelihood of gravitational wave recoil. By comparing simulation outcomes with observed features of a 2261 BCG, astronomers refine parameters and improve the predictive power of their models. The broader context of galaxy cluster evolution further enriches the narrative. Abell 2261, the cluster hosting a 2261 BCG, is itself a massive and complex system with intricate gravitational interactions among member galaxies. The cluster environment influences gas accretion, star formation rates, and dynamical friction processes that can affect central black hole behavior. Understanding these interactions is key to situating a 2261 BCG's peculiarities within the larger cosmic web. Intriguingly, the potential absence or displacement of a supermassive black hole raises questions about the fate of such objects after dramatic events. If ejected, a black hole might wander into galactic space, carrying with it stars and gas that serve as a faint beacon. Detecting such rogue black holes presents formidable challenges but offers a tantalizing prospect for uncovering hidden aspects of black hole populations. The ramifications extend to gravitational wave astronomy, an emerging frontier revolutionizing our understanding of cosmic events. While stellar mass black hole mergers have been observed, detecting signals from supermassive black hole coalescences remains a goal for future observatories like LISA. Observations of galaxies like A2261 BCG provide empirical targets that can validate and guide gravitational wave searches, bridging electromagnetic and gravitational observations. A2261 BCG stands at the crossroads of multiple disciplines: observational astronomy, theoretical astrophysics, cosmology, and gravitational wave physics. Its enigmatic core challenges us to reconsider foundational concepts and encourages the integration of diverse methodologies to approach cosmic mysteries. As research progresses, this giant galaxy with its mysteriously missing central black hole will continue to captivate scientists and the public alike, serving as a symbol of the ever-unfolding complexity and wonder of the universe. The case of A2261 BCG not only challenges our astrophysical understanding but also forces us to re-examine the fundamental processes that govern the life cycles of galaxies and their central supermassive black holes. To fully appreciate the significance of this galaxy's peculiar nature, it is essential to delve into the prevailing theories of black hole formation and growth within galaxies and how these processes are intertwined with galactic evolution on cosmic timescales. Supermassive black holes, typically millions to billions of times the mass of our Sun, are thought to grow primarily through two channels: accretion of gas and dust, and mergers with other black holes during galactic collisions. The center of a large elliptical galaxy like A2261 BCG usually hosts one such supermassive black hole, which profoundly influences the host galaxy's structure and star formation history. The energetic feedback from accretion processes, where the black hole consumes surrounding matter, regulates the inflow of gas, heating and expelling it in powerful jets and winds. This feedback mechanism is crucial to preventing runaway star formation, maintaining the delicate balance in the galaxy's life cycle. In the specific case of A2261 BCG, the lack of a detectable supermassive black hole in its core is a glaring anomaly. The core's enormous size and flat stellar density profile suggest a dramatic event in the galaxy's past, likely connected to the black hole's fate. One plausible scenario is that A2261 BCG experienced a major merger between two massive galaxies, each harboring its own supermassive black hole. Such mergers are violent cosmic episodes, where the black holes spiral inward under gravitational attraction and eventually coalesce. However, if the merging black holes emit asymmetric gravitational waves during their final coalescence, they can receive a recoil kick so powerful it ejects the newly formed black hole from the galactic center, an event sometimes called a gravitational wave recoil or black hole kick. This recoil can propel the black hole at thousands of kilometers per second, potentially removing it entirely from the galaxy's nucleus or even the galaxy itself. The resulting core, left devoid of its central massive anchor, expands as stars adjust their orbits, forming the unusually large, diffuse core observed in A2261 BCG. Observations of such a core can thus be indirect evidence of an ejected supermassive black hole. Further complicating the matter, the timescale over which such ejections and subsequent stellar reconfiguration occur is vast, on the order of hundreds of millions to billions of years. During this time, the galaxy's core relaxes, and the stellar density profile settles into the flattened configuration we observe today. This means the event that expelled the black hole could have happened long ago, and direct evidence of the black hole's current location might be elusive. Astronomers have attempted to locate the missing black hole by searching for signs of off-center activity or compact X-ray sources elsewhere in the galaxy. Such searches look for accretion signals, X-rays, radio emissions, or other high-energy signatures that might indicate a wandering black hole still feeding on gas. While some candidate sources have been identified, none has been conclusively linked to a displaced supermassive black hole in A2261 BCG, leaving the mystery unresolved. This raises the fascinating possibility that the black hole may be truly missing, or that it is a ghost, wandering in the intergalactic medium or hidden behind thick layers of dust and gas that obscure its emissions from our instruments. Alternatively, the black hole could be so inactive that it emits no detectable radiation, making it effectively invisible except for its gravitational influence, which becomes challenging to measure at the galaxy's center given current observational limits. The ramifications of such a discovery extend far beyond A2261 BCG. If supermassive black hole ejections are more common than previously thought, they would have significant implications for galaxy evolution models. The presence, or absence, of central black holes influences star formation rates, galaxy morphology, and the distribution of dark matter. Without a central black hole, the regulatory feedback mechanisms that shape galaxies may operate differently, leading to a more diverse range of galactic structures and behaviors than standard models predict. Moreover, the potential for rogue supermassive black holes wandering the cosmic landscape poses intriguing questions about the nature of the intergalactic medium, and the role these invisible titans play in shaping the universe. These wandering black holes could occasionally encounter and disrupt gas clouds, trigger star formation in unexpected locations, or merge with other black holes, producing gravitational wave signals detectable by future observatories. Understanding the fate of black holes in systems like A2261 BCG also intersects with the emerging field of gravitational wave astronomy. Future detectors, such as the Laser Interferometer Space Antenna, LISA, aim to observe low-frequency gravitational waves emitted by supermassive black hole mergers. Confirming the presence or absence of black holes in galaxies like A2261 BCG will help refine predictions about the frequency and characteristics of these gravitational wave events. On a broader scale, A2261 BCG challenges us to expand our observational strategies and develop new technologies. High-resolution spectroscopy, deep multi-wavelength imaging, and refined theoretical modeling must converge to peel back the layers of complexity surrounding this galaxy's core. This galaxy serves as a proving ground for next-generation instruments, pushing the limits of sensitivity and resolution. As astronomers continue to study A2261 BCG, the galaxy's story unfolds as a testament to the dynamic and sometimes violent processes that shape our universe. Its missing black hole is not just a gap in our observations but a beacon illuminating the profound and intricate dance of gravity, matter, and energy across cosmic time. The mystery beckons us to explore further, to ask bolder questions, and to embrace the unknown as a pathway to discovery. The story of A2261 BCG is ongoing, a cosmic riddle waiting to be solved, with each new observation and theory bringing us closer to understanding one of the universe's most intriguing anomalies. The enigma of A2261 BCG's missing central black hole stands as one of the most captivating puzzles in modern astrophysics. To grasp the full depth of this mystery, one must consider not only the physical phenomena that might have led to the disappearance, but also the technological and theoretical frameworks that underpin our search for understanding. Historically, the discovery of supermassive black holes at the centers of galaxies revolutionized our perception of galactic nuclei. These monstrous entities, often weighing millions or billions of times the mass of the Sun, anchor galaxies gravitationally and influence their evolution profoundly. The presence of a supermassive black hole is typically inferred through its gravitational effects on nearby stars and gas, as well as through energetic emissions produced by accretion processes. In giant elliptical galaxies like A2261 BCG, astronomers expect to find the most massive black holes, given their vast stellar populations and the likelihood of multiple merger events throughout their histories. Observations usually reveal dense cores where the gravitational pull of the black hole sculpts the stellar distribution, causing a concentration of stars and gas. However, in A2261 BCG, the opposite is true. Its core is unusually large and flat, lacking the steep density cusp that signals a massive black hole's gravitational dominance. The first detailed studies of A2261 BCG's core came from the Hubble Space Telescope's high-resolution imaging, which revealed a core spanning some 3,000 light-years, vastly larger than those of other galaxies of comparable size. This discovery raised immediate questions about the dynamics within this galactic heart. The large, diffuse core suggested a significant disruption, likely the result of past violent interactions. One prominent hypothesis centers around the phenomenon of black hole recoil following a merger. When two supermassive black holes merge, they emit gravitational waves, ripples in spacetime predicted by Einstein's general relativity. If these waves are emitted asymmetrically, they impart a kick to the resulting black hole, potentially ejecting it from the galaxy's center. Simulations indicate such kicks can reach speeds of thousands of kilometers per second, enough to propel a black hole beyond the escape velocity of even the most massive galaxies. If a 2261 BCG's central black hole was expelled in such a manner, the galaxy's core would react dynamically. Stars once tightly bound by the black hole's gravity would redistribute, creating the observed flat, low-density core. This process is known as core scouring, where the binary black hole's gravitational interactions eject stars before the final recoil event removes the black hole itself. The resultant core is thus a fossil record of the black hole's dramatic ejection. Supporting evidence for this scenario includes the detection of a few compact stellar clumps near the core, potentially remnants of the star cluster bound to the black hole at the time of ejection. These hypercompact stellar systems might trail the black hole as it moves through the galaxy or even beyond. Detecting such structures and measuring their dynamics can provide indirect confirmation of the black hole's fate. Yet, despite extensive searches, direct evidence of the black hole remains elusive. X-ray and radio observations, sensitive to the emissions from actively accreting black holes, have failed to reveal a convincing candidate. One explanation is that the black hole, if still present, is in a quiescent state, not feeding on surrounding matter and thus silent across the electromagnetic spectrum. Alternatively, the black hole may have traveled beyond the galaxy entirely, wandering through intergalactic space as a rogue object. Such a scenario introduces intriguing questions about the fate and detectability of displaced supermassive black holes. Without the dense stellar environment of a galaxy, accretion rates would plummet, rendering the black hole nearly invisible except through its gravitational influence. The implications of this phenomenon extend beyond the peculiar case of a 2261 BCG. If black hole ejections are frequent enough, they may influence the population statistics of supermassive black holes in the universe and impact models of galaxy evolution. The existence of naked supermassive black holes could represent a missing population, currently undetected due to observational limitations. Moreover, the physics of black hole mergers and recoils have profound consequences for gravitational wave astronomy. Observing these events directly through gravitational waves would provide unparalleled insights into the extreme conditions of spacetime and the behavior of gravity under the most intense environments. Upcoming missions like the Laser Interferometer Space Antenna, LISA, set to launch in the 2030s, promise to open this new observational window. LISA will be sensitive to low-frequency gravitational waves emitted by merging supermassive black holes, potentially catching recoil events similar to what might have occurred in a 2261 BCG. Coupled with electromagnetic observations, this multi-messenger approach will revolutionize our understanding of black hole physics. In the meantime, astronomers continue to push the boundaries of current technology to uncover clues hidden within a 2261 BCG. High-resolution spectroscopic studies aim to measure subtle stellar motions that could betray the presence of a displaced black hole. Deep imaging in multiple wavelengths seeks faint signatures of accretion or jet activity. The integration of data across the electromagnetic spectrum and advances in computational modeling stand at the forefront of this quest. A 2261 BCG's mystery also inspires broader reflections on the nature of the universe. It reminds us that even in regions where we expect certainty, like the centers of massive galaxies, there remain surprises that challenge assumptions and spark new questions. The universe, vast and complex, continues to reveal its secrets, only gradually, each discovery deepening the sense of wonder. The story of a 2261 BCG and its missing black hole is emblematic of the scientific journey itself, a path marked by curiosity, unexpected findings, and the relentless pursuit of knowledge. As observations improve and theories evolve, this enigmatic galaxy will remain a beacon guiding us toward a fuller understanding of cosmic evolution and the mysterious objects that inhabit our universe. The more we delve into the enigma of A2261 BCG, the more we find ourselves standing at the precipice of the unknown, staring into a cosmic mystery that defies our expectations. This is not just the tale of a single galaxy with a curious feature, it is a lens through which we examine the very mechanisms of the universe itself. The story of the missing black hole from the heart of A2261 BCG compels us to reevaluate what we know about the life cycle of galaxies, the rules that govern supermassive black hole formation, and the cataclysmic forces unleashed during mergers and galactic interactions. To understand the scale of this phenomenon, consider what it means for a galaxy to have a core as large as the one found in A2261 BCG. At approximately 3,000 light-years across, its core is more than twice the size of other similarly massive galaxies. This size suggests not just a passive feature of its structure but an active history of violent interactions. Scientists believe that this unusually large and diffuse core is not a stable or long-term feature, but rather the aftermath of extreme gravitational disturbances, possibly involving not one, but multiple supermassive black holes over time. The role of dynamical friction becomes central here. In the early universe, galaxies collided frequently, and their central black holes would have spiraled toward one another due to energy loss through interactions with surrounding stars, a process known as dynamical friction. Eventually, the black holes form a binary system. This binary can further harden as it slingshots nearby stars away, losing angular momentum in the process. Over time, these repeated interactions evacuate the galactic core, lowering the stellar density, and creating the type of flattened core observed in A2261 BCG. This theory also feeds into the idea that A2261 BCG's central black hole may not have merely vanished or ceased accreting matter, it might have been violently kicked out. This recoil event could explain not only the absence of an active galactic nucleus, AGN, but also the symmetry of the core, which lacks the asymmetry typically expected from recent mergers. If the black hole was ejected at high speed, dragging along only a small cluster of stars in its gravitational grip, it would be nearly invisible at intergalactic distances. Another consideration is the possible interaction with dark matter. A massive object like a black hole traveling through a dark matter halo could be slowed by dynamical friction with that halo, potentially stalling its escape or causing it to settle into a new, off-center orbit within the galaxy. But in A2261 BCG's case, no such off-center black hole has yet been detected, leaving open the possibility that it continued onward into the void. Efforts to detect this black hole have included the use of the Chandra X-ray Observatory, which searched for high-energy emissions that would signal accretion onto a black hole. But these efforts came up empty. No signature was found in the core, nor in the clumps of stars around it, suggesting that if the black hole is still within the galaxy, it must be accreting at an incredibly low rate, so low that even our most sensitive instruments cannot detect it. Alternatively, if it's outside the galaxy altogether, drifting alone through intergalactic space, its emissions may be so faint and diffuse that they are completely beyond our current capabilities. Meanwhile, the Hubble Space Telescope has continued to observe the central region in detail, mapping out the distribution and velocity of stars. From these data, scientists can infer whether an unseen gravitational mass might be tugging at nearby stars, thus betraying the presence of a black hole. But so far, the motions of the stars do not suggest any such presence. This lack of evidence doesn't rule out the black hole entirely, but it forces us to consider increasingly exotic explanations. For instance, some have proposed that A2261 BCG may host an unusually large population of intermediate mass black holes, each too small to dominate the core but collectively influencing the stellar distribution. Others suggest that an undetected binary black hole might be orbiting within the core, with the black holes so close to each other and so quiescent that they remain undetected by current instruments. Still others speculate on entirely new physics, such as modifications to general relativity or alternative compact objects that mimic black holes but behave differently under extreme conditions. These possibilities bring up deep theoretical questions. Could there be mechanisms by which supermassive black holes evaporate or collapse into exotic matter states, leaving no trace behind? Could quantum gravitational effects play a role in the final fate of these monstrous entities, perhaps dissipating them in a way that evades traditional observation? Or could our models of galactic evolution and black hole formation be fundamentally incomplete, requiring a rethinking of the processes that build up mass and galactic centers? The search for answers doesn't end with observations of A2261 BCG alone. Astrophysicists are now looking to other galaxies with similarly large cores for comparison. Are there more examples of missing black holes? Are large cores always linked with galactic collisions and binary black hole dynamics? Could we be seeing the aftermath of black hole ejections more often than we realize, simply missing the smoking gun in each case? This is where simulations come in. Using powerful supercomputers, researchers model the mergers of galaxies and the behavior of black holes under extreme gravitational forces. These simulations produce predictions for what such galaxies should look like if they underwent specific types of mergers or recoil events. Comparing these virtual galaxies to A2261 BCG allows scientists to constrain the likely history of its core, narrowing down the events that could have led to its current appearance. Such simulations also factor in dark matter distributions, star formation rates, gas dynamics, and feedback from AGN activity. These variables are crucial because they can drastically alter the final structure of a galaxy. For example, if A2261 BCG once hosted a powerful AGN that blew out large amounts of gas, it could have further hollowed out the core and shut down star formation, contributing to the diffuse appearance we see today. Even broader than this is the implication for cosmology. If supermassive black holes can be ejected from galaxies, it might help explain certain discrepancies in the observed black hole mass function across different environments. It may also contribute to the population of wandering black holes, those not bound to any galaxy and moving silently through the universe. These objects are nearly impossible to detect, but their gravitational influence might one day be measurable through microlensing or gravitational wave signals. And so, A2261 BCG becomes not just a case study in galactic structure, but a window into the hidden population of cosmic nomads. It asks us to consider how many other galaxies might be missing their cores, how many black holes may roam unbound through space, and how many secrets lie just out of reach of our instruments. As we continue to explore this remarkable galaxy, future missions like the James Webb Space Telescope, JWST, and LISA promise new avenues of detection. JWST's infrared capabilities can peer through dusty regions and detect cooler objects, while LISA may one day hear the space-time echoes of ancient mergers and recoil events. Each of these tools brings us closer to resolving the riddle of A2261 BCG. But even as we inch toward answers, this galaxy reminds us that the universe is not obligated to make sense within our current frameworks. It challenges us to expand those frameworks, to ask deeper questions, and to remain open to the possibility that our most trusted theories may one day be rewritten by discoveries yet to come. The mystery of A2261 BCG doesn't just live within the boundaries of its enormous core or the silence left by its absent central black hole. It extends outward into the vast conversation around cosmic structure and the unseen narratives of galaxy evolution. In many ways, this galaxy serves as a focal point for our deepest questions about the forces that shape the universe, not merely as curiosities, but as governing principles that define how matter and energy interact across billions of years and inconceivable distances. What makes the absence of the central black hole even more captivating is that, in virtually every model of galaxy formation we possess, such a black hole is not only expected, it's central to the identity of the galaxy. The presence of a supermassive black hole in the heart of a galaxy is more than just coincidence. It's part of a well-established relationship known as the M-sigma relation. This empirical correlation links the mass of a galaxy's central black hole to the velocity dispersion of the stars in its bulge. In simpler terms, it implies that galaxies and their black holes co-evolve, growing together over cosmic time. So when A2261 BCG fails to reveal its central black hole, despite its massive size and large bulge, it creates a rift in the standard understanding. If the central black hole was never there, how did the galaxy grow to such immense proportions without violating the m-sigma relation? If it was there and is now missing, what kind of event was powerful enough to separate the black hole from the very structure it helped to shape? And if it is still there, buried, dormant, or undetectable, what secrets lie within the surrounding matter that conceal it so effectively? One possibility that astronomers have explored involves the concept of a gravitational recoil. When two black holes merge, typically during a galactic collision, the resulting black hole emits gravitational waves. These waves are not always emitted symmetrically, especially if the two merging black holes differ in mass or spin. The imbalance in wave emission can produce a net force that physically propels the merged black hole in a specific direction, effectively kicking it away from the center of the galaxy. This is not science fiction, it's a prediction of general relativity, confirmed by simulations and supported by indirect observational evidence. Theoretical models suggest that in extreme cases, these kicks can reach speeds of thousands of kilometers per second, more than enough to eject a black hole from the gravitational hold of its galaxy. If such a kick occurred in A2261 BCG, it could have sent its central black hole hurtling into the dark vastness of intergalactic space, dragging with it only a few tightly bound stars as a faint remnant of its former kingdom. And yet, despite the elegance of this explanation, observational data have not yet confirmed the presence of such a runaway black hole. Multiple candidate objects near the core have been examined with both optical and X-ray telescopes, and none have shown definitive signs of hosting a supermassive black hole. They lack the telltale X-ray emissions, gravitational influence, or spectral lines indicative of high-energy accretion. This raises further questions. If the black hole was ejected, where is it now? If it wasn't, then what event caused the expansion of the core and the peculiar symmetry in stellar distribution? Another intriguing line of inquiry concerns the role of dark matter. Though invisible, dark matter constitutes the vast majority of the galaxy's mass and dictates much of its gravitational behavior. If the distribution of dark matter in A2261 BCG is unusual, say, more diffuse in the core, it could affect the dynamics of stars and black holes differently than expected. It's even possible that a dark matter-dominated core might mask the gravitational signature of a black hole, making it harder to detect through conventional means. Additionally, consider the idea of a relic galaxy. These are ancient systems that formed early in the universe's history and then experienced relatively little activity afterward. If A2261 BCG is such a relic, it may have followed a growth path distinct from typical elliptical galaxies. It might have gained mass through accretion of smaller galaxies, rather than via large mergers. In this scenario, the supermassive black hole could have formed under different conditions, or even failed to form at all. This pushes us to reconsider what we mean by normal galactic evolution. Are we making too many assumptions based on the limited sample of galaxies in our cosmic neighborhood? Is it possible that the conditions necessary for black hole formation vary more than we think? If so, the absence of a central black hole in A2261 BCG might not be an anomaly. It might represent an alternative pathway of galactic life. The observational tools at our disposal continue to improve, and with them, our understanding deepens. One of the most promising avenues for resolving the A2261 BCG mystery lies in gravitational wave astronomy. Facilities like LIGO and Virgo have already detected mergers of stellar mass black holes, but future space-based observatories like LISA will be sensitive enough to detect the gravitational waves produced by supermassive black hole mergers. These waves can travel across the universe unimpeded, providing direct insight into the dynamics of the varied processes that may have occurred in A2261 BCG. If a merger followed by a gravitational recoil did indeed happen there, its gravitational footprint could still echo across space-time. Detecting such a signal would not only solve the riddle of the missing black hole but also serve as a profound confirmation of our theoretical models of strong field gravity. Meanwhile, astronomers are casting their nets wider, searching for galaxies with similar characteristics. If A2261 BCG is not alone, then perhaps it is part of a broader class of galaxies that have undergone extreme events, resulting in core expansion and black hole displacement. Cataloging and comparing these galaxies may uncover patterns or statistical clues that reveal the underlying mechanisms at play. And so, the pursuit continues, not just of a missing black hole, but of a greater understanding of the universe itself. A 2261 BCG is a monument to cosmic mystery, a structure that embodies the grandeur and complexity of galactic evolution. Its empty core is a mirror in which we see the limits of our knowledge, and its silence challenges us to listen more closely to the whispers of the cosmos. The search for its central black hole may take years, decades, or even longer. It may require tools that have not yet been invented, insights not yet conceived. But with each new observation, each theory tested and refined, we inch closer to uncovering the truth. A 2261 BCG stands as a sentinel in the sky, holding secrets that will one day reshape our understanding of how galaxies grow, how black holes move, and how the universe tells its stories. In the immense narrative of cosmic evolution, a 2261 BCG is not merely a character with a missing trait. It is a riddle wrapped in billions of stars, a conundrum stretching across millions of light years, and a challenge to nearly everything we think we understand about how galaxies work. To appreciate the true depth of this mystery, we must first pause to examine how galaxies like a 2261 BCG are typically structured, how their centers form, and why the absence of a supermassive black hole is not just unusual, it's revolutionary. In conventional galactic models, the formation of a central bulge in an elliptical galaxy like a 2261 BCG is intimately tied to the presence of a supermassive black hole. These behemoths, with masses ranging from millions to billions of times that of our Sun, act as gravitational anchors, orchestrating the motion of stars, regulating the inflow of gas, and even shaping the star formation rates through intense feedback mechanisms. The jets and winds that erupt from their energetic cores can influence galactic scales, heating interstellar matter and halting the collapse of gas clouds, effectively governing how galaxies grow and change. A galaxy with no such center, then, is like a solar system with no sun. It calls into question not just how the structure remains stable, but how it was built in the first place. This is where the sheer size and luminosity of a 2261 BCG becomes even more baffling. With a stellar mass estimated to be over 10 times greater than that of the Milky Way, and a core extending more than 10,000 light-years across, it stands as one of the most massive and diffuse galactic cores ever observed. Ordinarily, such central cores are densely packed with stars, orbiting rapidly around a hidden central mass, the black hole. In a 2261 BCG, however, the core is strangely diffuse, not just large but eerily symmetric, with no obvious dense concentration at the heart. This symmetry might suggest a relaxed, mature system, but the lack of a gravitational center implies recent turmoil, like the aftermath of a cataclysmic event that left the core stretched and hollowed. Astronomers have employed every available observational strategy to search for signs of the missing black hole. Optical imaging from the Hubble Space Telescope reveals a smooth, almost featureless glow across the core, no signs of intense gravitational lensing, no dense stellar knots that might betray the presence of an unseen mass. Radio observations, which often pick up the emissions of accreting material falling into black holes, yield silence. X-ray telescopes, which could detect high-energy phenomena associated with compact, massive objects, return similarly empty-handed results. One explanation, albeit extraordinary, is that the central black hole has been ejected entirely. This idea is supported by simulations that show how gravitational wave recoil can remove a black hole from the heart of a galaxy. If two massive black holes merge with asymmetric spins or mass ratios, the newly formed singularity can receive a gravitational kick. This kick, depending on the conditions, could be strong enough to overcome the gravitational pull of even a massive galaxy and fling the black hole out into intergalactic space. A black hole moving through the cosmos would not be entirely invisible. If accompanied by a handful of bound stars, perhaps those closest to it at the time of ejection, it would resemble a hypercompact stellar system. Such a system would be difficult to detect, particularly in a crowded field like the core of a 2261 BCG. but not impossible. So far, though, astronomers have only identified several candidate regions that show unusual motion or brightness, none of which have definitively confirmed the presence of a runaway black hole. Let's delve deeper into the observational footprint of such a black hole. Theoretically, a supermassive black hole ejected from the center of a galaxy could maintain a small accretion disk for some time, especially if it passed through regions of higher gas density. This accretion disk would emit radiation, particularly in the X-ray and radio wavelengths, potentially allowing for detection. Moreover, the stars gravitationally bound to the runaway black hole would orbit it rapidly, creating a localized region of high-velocity dispersion that could be observed through precise spectroscopic measurements. If such an object exists, it would be like a ghost king in exile, a black hole wandering alone, once the monarch of its galaxy, now cast adrift in the intergalactic sea. Finding such an entity would not just solve the mystery of A2261 BCG, but would also offer the first direct observational evidence of black hole recall, confirming a major prediction of general relativity and black hole physics. Another avenue of investigation centers on the possibility that the black hole is still there, just dormant. In this scenario, the black hole could have entered a prolonged period of quiescence, in which little or no material is falling into it, making it virtually invisible to our instruments. This could happen if the galaxy exhausted its central gas supply, or if feedback processes from earlier active phases swept material out of the core. Without an accretion disk, a supermassive black hole is almost entirely dark, its presence detectable only through its gravitational influence on nearby stars. But even this raises challenges. A central black hole with a mass of several billion solar masses would still cause noticeable perturbations in stellar velocities. These could be detected through detailed spectroscopic analysis, measuring the Doppler shifts of stars as they orbit. While some data hint at irregularities, they are not conclusive. In fact, the velocity dispersion in the core appears too low to suggest the presence of such a massive central object, yet another anomaly that feeds the enigma. Adding further intrigue is the age of the galaxy. A 2261 BCG resides at a redshift of approximately 0.224, which places it at a look-back time of about 3 billion years. This means we are seeing the galaxy as it existed when the universe was roughly 10.5 billion years old. By that point in cosmic history, most massive galaxies had already undergone major mergers and settled into relatively stable forms. If a 2261 BCG experienced a recent black hole merger or ejection, it implies a late-stage event in its evolution, an unexpected twist in its ancient life. This opens a larger question: could a 2261 BCG be part of a new class of galaxies, those whose central black holes have been ejected or lost due to gravitational interactions? If so, there may be more such galaxies hiding in plain sight. Identifying them would require a systematic survey of galaxy cores, looking for telltale signs: large, flat cores with low stellar densities, absence of central velocity peaks, lack of high-energy emissions, and strange symmetries. Theoretically, this class could reshape our models of galactic feedback, bulge formation, and dark matter distribution. It would challenge the assumption that black hole growth and galaxy evolution are always tightly coupled. Perhaps in some rare but real scenarios, galaxies can continue to thrive even after losing their most dominant gravitational component. It is also possible that the missing black hole lies just outside the visible core, its gravitational presence masked by the diffuse structure of the galaxy. Imagine a black hole orbiting the galaxy's center in a wide ellipse, the result of a failed merger or slingshot interaction. Its mass could be comparable to that of the galactic core, and yet its current position could place it hundreds or even thousands of light-years from the center, well outside the range of conventional core-focused observations. This possibility opens new doors for off-center searches. Astronomers may need to extend their instrument's focus, looking not just at the heart of the galaxy, but across its inner halo. This is an observational challenge, but not an impossible one. With high-resolution spectroscopy and adaptive optics, it's feasible to map the stellar motions across a wider swath of the galaxy, searching for local gravitational anomalies or regions with unexpected velocity dispersions. The mystery of A2261 BCG forces us to think beyond traditional models. It demands a new framework for understanding the interplay between stars, black holes, and the invisible scaffolding of dark matter. It also beckons us to explore the outer boundaries of our observational tools, to refine our simulations, and to widen our search criteria for anomalies in galactic cores. At its heart, this is not just a story of absence. It is a story of discovery, of how a silent core speaks volumes, how missing mass reveals hidden forces, and how the universe, in its infinite complexity, always has more to teach us than we thought possible. As astronomers and physicists continue to investigate A2261 BCG, they're not merely piecing together a local mystery, they're pushing the boundaries of cosmic understanding. The case of the missing supermassive black hole is no longer just about one galaxy. It's about uncovering whether our assumptions about the universal connection between galaxies and black holes are truly universal, or if exceptions like A2261 BCG point to a deeper, more nuanced reality. The notion that a galaxy can exist, thrive, even, without its central black hole invites speculation about alternative models of galactic stability. Could it be that the massive gravitational potential of the galaxy's stellar population and dark matter halo is sufficient to maintain its structure? If so, this would challenge the long-standing view that black holes are the central regulators of galactic dynamics. Additionally, the strange size and flatness of A2261 BCG's core suggest a dramatic past. One leading theory posits that the galaxy underwent a major merger, perhaps between two enormous elliptical galaxies, each harboring its own supermassive black hole. In the aftermath, those black holes spiraled inward, interacting gravitationally, eventually forming a binary system. If this binary merged and recoiled, as theorized, the resulting kick could have thrown the newly formed black hole far from the center, or entirely out of the galaxy. To understand the physics behind this, consider the nature of gravitational wave recoil. When two black holes merge, the gravitational waves they emit are not always symmetrical. Any imbalance in this emission leads to a recoil. The merged black hole is physically pushed away from its original position. In most cases, this recoil is not strong enough to eject the black hole from the galaxy entirely, but in galaxies with low central escape velocities, or in cases of highly asymmetrical black hole mergers, the kick can be strong enough to do just that. A 2261 BCG, due to its low central stellar density and unusual core structure, could be just such a galaxy. And if its supermassive black hole was ejected, it might still be traveling through intergalactic space, a rogue singularity moving silently, dragging a swarm of tightly bound stars with it. Detecting such an object would be like finding a cosmic ghost ship, brilliantly revealing and fundamentally paradigm-shifting. But the implications don't stop there. If gravitational wave recoil events are this powerful, and if they occur more frequently than we think, it might mean that many galaxies have lost their central black holes and continue to evolve without them. This would explain not only anomalies like A2261 BCG, but also certain ultra-diffuse galaxies with strange kinematics and low central masses. To explore these possibilities, upcoming observatories like the James Webb Space Telescope, already operational as of 2022, and future instruments like the Nancy Grace Roman Space Telescope and the Extremely Large Telescope, are key. These will allow astronomers to conduct deeper, more sensitive surveys of galaxy cores, as well as search for off-center or isolated black holes through gravitational lensing, stellar dynamics, or faint electromagnetic signatures. Furthermore, as gravitational wave astronomy matures, particularly with projects like the Laser Interferometer Space Antenna, LISA, set to launch in the 2030s, we may directly detect the waves from supermassive black hole mergers. These signals will not only confirm the existence of such events but will also offer precise measurements of the recoil velocities, helping scientists estimate how often black holes are actually ejected from their host galaxies. Meanwhile, simulations of galaxy mergers continue to grow in sophistication. Cosmological models now account for multiple generations of black hole mergers, feedback effects from star formation and AGN activity, and even the dynamical friction that influences how black holes settle, or fail to settle, into the centers of merged galaxies. These simulations suggest that while most galaxies retain their central black holes, a notable fraction may lose them through the very processes that build galactic mass in the first place. In this way, A2261 BCG becomes a linchpin in a much broader cosmic story. It's not just a mystery, it's a piece of a larger puzzle about the birth, death, and rebirth of galaxies. Its silent, hollow core may be the scar left behind by an ancient, cataclysmic event. And like any scar, it tells a story, not only of trauma and transformation but also of survival. The core of A2261 BCG, with its strange symmetry, faint starlight, and absent anchor, invites us to rethink how galaxies live and change. It tells us that perhaps not all galaxies require a central black hole to maintain cohesion. Perhaps galactic evolution is more flexible than we imagined, capable of adapting, reforming, even thriving after losing what we once thought was its most crucial component. A2261 BCG is a monument to the unknown. It stands at the intersection of observation and imagination, of theory and possibility. And as we continue to study its depths, we are not just unraveling a galactic anomaly, we are redefining what it means to be a galaxy in a universe full of surprises. In light of everything A2261 BCG represents, one cannot help but marvel at the cosmic choreography that may have unfolded within its borders. If the supermassive black hole was truly ejected, this galaxy has not only witnessed an incredibly rare event, but has also preserved the aftermath in a way that modern instruments can probe, leaving behind a galactic crime scene frozen in time. The lingering question then becomes, where is the black hole now? If the black hole was truly kicked from the center due to gravitational recoil, then it could still be somewhere within the galaxy's halo, or even far beyond, racing through intergalactic space with a velocity of several thousand kilometers per second. Detecting such a runaway object is no simple task. A black hole does not emit light unless it's actively accreting matter. However, the gravitational influence it exerts on nearby stars, or a tightly bound entourage of stars it might have taken with it, could serve as indirect evidence. Astronomers are on the lookout for such off-center luminous knots of stars, possibly speeding through space like celestial exiles, trailing clues behind them. Moreover, the peculiar structure of A2261 BCG's core supports this runaway theory. Most elliptical galaxies have a brightness profile that steeply rises toward the center, consistent with the presence of a central gravitational attractor. But A2261 BCG's core is anomalously large and flat, suggesting that the core was once carved out by a pair of spiraling supermassive black holes that ejected stars through gravitational slingshot interactions, a common effect in binary black hole dynamics. This process, called core scouring, leaves a visible signature in a galaxy's light profile, and A2261 BCG exhibits one of the most extreme examples ever observed. Interestingly, core scouring not only helps support the idea of a past merger, but it also ties into our broader understanding of hierarchical galaxy formation. In the hierarchical model, galaxies form through repeated mergers of smaller systems. Each merger adds not only stars and gas, but potentially a central black hole as well. These black holes migrate toward the center of the new, larger galaxy, often forming binaries, which may eventually merge themselves. The ejection of the resulting black hole through gravitational recoil, as suspected in A2261 BCG, is the rare but natural outcome of this cosmic process. This leads us to a philosophical and observational crossroads. For decades, astronomers considered central black holes to be essential parts of galaxy evolution. Their feedback, jets, winds, and radiation, regulates star formation and prevents galaxies from overgrowing. Without this central regulator, it was thought galaxies would spiral into chaotic starburst activity. But A2261 BCG challenges this dogma. It is massive. It is luminous. And it continues to exist and evolve despite what appears to be a missing supermassive black hole. Could there be other mechanisms at play, perhaps involving dark matter halos or distributed feedback from other sources, that allow a galaxy to self-regulate? Or does the absence of an active galactic nucleus merely mean that the black hole is dormant or displaced, rather than absent? These are not trivial questions. They strike at the heart of how we model galaxies, simulate cosmic structure formation, and even interpret the role of black holes in shaping the universe. Adding another layer of mystery is the unusual symmetry of A2261 BCG's core. While its flatness suggests a disrupted center, the lack of any lopsided features is strange. If a supermassive black hole had been ejected, wouldn't there be visible structural asymmetries? Wouldn't we see signs of recent disturbance, like off-center stellar populations or remnants of the binary core? In A2261 BCG, everything appears oddly serene. It's as if the galaxy has been given ample time to smooth out the chaos and return to equilibrium. This points to the possibility that the merger and subsequent black hole ejection happened billions of years ago, giving the galaxy enough time to stabilize, yet still retaining the enormous core as a fossilized imprint of that ancient violence. The search for the displaced or ejected black hole is ongoing. Using instruments like the Hubble Space Telescope, the Chandra X-ray Observatory, and ground-based observatories with adaptive optics, astronomers are scanning the regions around A2261 BCG for telltale signs, faint X-ray emissions, compact stellar clusters, or even gravitational lensing effects. So far, several off-center knots of light have been identified within the galaxy. These could be star clusters, or they could be the traveling companions of a runaway black hole. Yet none have definitively revealed the presence of a singularity. This scientific stalemate is compelling. It demonstrates not only the complexity of the universe, but the humility required of those who study it. Sometimes, the absence of evidence becomes the most profound evidence of all, forcing us to question assumptions, reframe hypotheses, and develop new models. In this way, A2261 BCG is not just a galaxy. It is a challenge. A question mark painted on the canvas of the cosmos. It is also an ideal target for next-generation observatories. The James Webb Space Telescope, for instance, can peer into the core of galaxies with unprecedented resolution in the infrared. If there are subtle signs of black hole interactions, or if a wandering compact object is lurking nearby, JWST could detect it. Likewise, LISA, the Laser Interferometer Space Antenna, will revolutionize our ability to detect gravitational waves from supermassive black hole mergers. If a merger occurred in A2261 BCG in the past few billion years and released gravitational waves, those ripples may still be detectable as part of the stochastic background, or even as a resolved signal if similar events happen nearby. In parallel, large-scale surveys like those planned for the Vera C. Rubin Observatory will monitor the sky for transient events, like tidal disruption flares from rogue black holes devouring stars, or subtle proper motions that could indicate an off-center massive object in motion. These efforts, combined with theoretical simulations and machine learning analysis, may eventually reveal what happened to the black hole in A2261 BCG. Until then, the galaxy stands as a testament to the dynamic and often violent nature of the cosmos. Its smooth halo, enormous mass, and gaping core are all that remain of an event that may have occurred billions of years ago, an event that reshaped not only its structure, but our understanding of black holes and galactic evolution itself. But what if the black hole isn't missing at all? What if it's just hiding in plain sight, cloaked in layers of interstellar dust or embedded so deeply in the galactic core that even our most precise instruments can't distinguish it from surrounding matter? This alternate theory suggests that the black hole in A2261 BCG may not have been ejected at all. It may still be at the center, simply in a dormant, ultra-quiet phase. Such a scenario would explain the lack of strong X-ray or radio emissions. Black holes only radiate when actively accreting matter, and in the vacuum of deep space, even a supermassive black hole can sit in silence for millions of years. To test this, astronomers have attempted to probe the central dynamics of A2261 BCG using velocity dispersion measurements. This involves observing how stars move in the inner regions of the galaxy, especially how their speeds change as one approaches the core. If a massive object is lurking there, it should noticeably influence stellar velocities. The results, however, have been inconclusive. While some measurements show slight anomalies that could hint at a hidden mass, the core is unusually diffuse and extended, making precise calculations difficult. Instead of a sharp gravitational pull at the very center, there's a broad, almost flattened mass distribution, another clue that something is different here. What makes the case even more intriguing is how this galaxy fits within the broader population of brightest cluster galaxies, BCGs. These are typically the largest and most massive galaxies in the universe, residing at the centers of galaxy clusters. They're surrounded by a swarm of satellite galaxies and bathed in the hot, X-ray emitting gas of the intracluster medium. BCGs are believed to grow via mergers over cosmic time, often cannibalizing smaller galaxies in their vicinity. With each merger, their central black holes should grow as well, resulting in a direct correlation between galaxy mass and black hole mass. But A2261 BCG throws a wrench in that narrative. Despite being among the most massive known BCGs, its black hole, if it exists at all, has never been detected. This disparity calls into question the supposed one-to-one relationship between galactic mass and black hole size. Could this imply that massive galaxies can, under some conditions, exist without an active or even present supermassive black hole? If so, what role did those black holes really play in galaxy formation to begin with? This opens up the possibility of alternative feedback mechanisms in massive galaxies. Perhaps A2261 BCG was shaped by environmental factors, like interactions with the hot intracluster medium or with dark matter structures, more than by its central black hole. Perhaps stellar feedback, supernova winds, or gas dynamics played a greater role in regulating its growth than previously thought. Or maybe the missing black hole is just one case in a broader class of outliers we have yet to understand fully. On the other hand, consider the sheer power of gravitational recoil, which lies at the heart of the black hole ejection theory. When two black holes spiral toward each other and merge, they radiate gravitational waves, a phenomenon confirmed by LIGO's detection of black hole mergers in 2015. If the waves are emitted asymmetrically, which they often are due to differences in mass or spin between the merging black holes, the remnant can receive a kick, like the recoil of a gun firing a bullet. The magnitude of this kick depends on various factors, including spin orientation and orbital eccentricity, but in extreme cases, it can reach several thousand kilometers per second. A black hole kicked at such a speed could easily escape the gravitational grip of even the most massive galaxies, including A2261 BCG. It would become a rogue, drifting silently through intergalactic space, perhaps still trailed by a cluster of bound stars that orbit it tightly, creating a compact system that resembles a star cluster but behaves strangely. This hypothetical, hypercompact stellar system is another target for observational efforts. It would appear as a small, faint object, potentially moving rapidly through space, an unusual signature that may one day betray the hiding place of A2261 BCG's missing giant. Adding to the mystery are numerical simulations that aim to recreate galaxies like A2261 BCG. By inputting various parameters, merger histories, black hole dynamics, dark matter distributions, cosmologists attempt to replicate its current state. Some models produce similar cores only when a central black hole is ejected, lending support to the recoil hypothesis. Others can replicate the observed core profile without requiring an ejected black hole, instead invoking long periods of dormant activity or unusual formation histories. These models help us understand what's possible, but they're only as good as the assumptions they're built on. And that's where we find ourselves, with a galaxy that defies expectations, whose heart seems empty yet whose body remains massive and luminous. It challenges our understanding of galactic cores, supermassive black hole formation, feedback processes, and gravitational wave recoil mechanics. It invites astronomers to look deeper, theorists to rethink their models, and observers to invent new methods of detection. In a cosmic sense, A2261 BCG is like a ghost story. It's the tale of a colossal galaxy with a gaping wound where its heart should be, a quiet testament to something that once was, or perhaps still is, hidden behind layers of time and space. Whether the black hole was flung into the void, buried in silence, or never existed in the way we imagined, it has already reshaped our understanding of how galaxies live, evolve, and die. And so the search continues, not just for a single black hole, but for a deeper truth about the universe itself. Every observation of A2261 BCG, every attempt to measure its mass or analyze its light, adds another brushstroke to the portrait of one of the cosmos's most fascinating enigmas. Perhaps someday, the veil will lift. Perhaps a glimmer of radiation or an unexpected stellar motion will reveal the black hole's hiding place. Until then, we are left with the silence of a massive galaxy, and the echo of a mystery stretching across billions of light years. The deeper we venture into the strange, diffuse heart of A2261 BCG, the more we are reminded of how much the universe still guards its secrets. Even with the most advanced instruments known to humanity, space-based observatories like Hubble, Chandra, and now the James Webb Space Telescope, there are still regions of the cosmos that seem to whisper just out of reach, just beyond the edge of our scientific grasp. The missing supermassive black hole in A2261 BCG may well be the most tantalizing of these whispers, not an absence, but a statement, a challenge written into the very fabric of cosmic evolution. Imagine standing at the core of A2261 BCG. While this is, of course, a mental exercise, no human could possibly survive in the extreme temperatures and vacuum of intergalactic space. Let's place ourselves hypothetically at the heart of this galactic titan. You'd be surrounded by the faint, ancient glow of stars stretching in every direction, billions of them spread over a colossal expanse. But unlike the bustling, tightly packed centers of typical galaxies, the core here feels open, eerie, vast. There is no dominant gravitational monster pulling everything in. Instead, you drift, unanchored, through a central void over 10,000 light-years across, a gap more than twice the diameter of our own Milky Way's central bulge. This alone sets A2261 BCG apart. It has the largest galactic core ever observed. Such a sprawling core isn't just an astronomical footnote. It's the forensic fingerprint of the galaxy's past. Cores this large are typically created during a galaxy merger, when the central black holes of each colliding galaxy spiral toward each other and interact. As they dance closer, their powerful gravity flings stars away from the center, creating a depleted core, what astronomers call a core scouring event. The more massive the black holes, the more dramatic the core they carve out. In A2261 BCG, the vast size of the core implies a history of dramatic, large-scale mergers. But if those mergers happened, and if, as theory suggests, the galaxies that merged each had central black holes, then the resulting black holes should be even larger and easily detectable. Yet there is silence. No trace. No radiation. No gravitational footprint that can be decisively attributed to a black hole with a mass in the billions of solar masses. This is not simply curious, it is disruptive to existing galactic evolution models. Some astronomers have speculated that the merged supermassive black hole received a strong enough gravitational kick to eject it from the core entirely. The energy required for this kind of gravitational recoil is enormous, but not outside the realm of physics. When two black holes spiral together and merge, gravitational waves are emitted unevenly, and this imbalance can push the newly formed black hole like a rocket, sending it hurtling through space. The precise magnitude of this kick depends on a complex interplay of parameters, including the spin, orientation, and mass ratio of the black holes. In the most extreme simulations, recoil velocities can reach up to 5,000 km per second, fast enough to escape any galaxy in the universe. If A2261 BCG's central black hole was kicked out in this way, it would now be drifting alone in space, carrying with it a tight cluster of stars that were bound to it at the time of ejection. Such objects, dubbed hypercompact stellar systems, are theoretically predicted, but incredibly difficult to detect due to their small size and faintness. Searching for them is like looking for a single firefly in a continent-sized fog. Interestingly, there have been candidate detections of such compact systems in other galaxy clusters, though none conclusively linked to an ejected supermassive black hole. In A2261 BCG's case, a few unusually bright and compact sources have been observed near the core, objects that could, in theory, be associated with a wandering black hole. But even these are ambiguous. They might be unusually bright star clusters, background galaxies, or simply anomalies caused by intervening dust and gas. Without stronger observational evidence, the theory remains a tantalizing possibility rather than a confirmed reality. This leads to the next major hypothesis. Perhaps the black hole isn't gone, just invisible. It could be heavily obscured by interstellar dust, hidden within a dense cloud of gas, or shrouded by the very stars that make up the galaxy's core. If the black hole is not currently accreting matter, it would be nearly impossible to detect through conventional means. Black holes are dark by nature. They don't emit light themselves, only the matter that falls into them does. And in the vast, low-density environment of A2261 BCG, there might not be enough gas or dust falling inward to light up the accretion disk. The challenge then becomes one of detection. Astronomers are now looking to next-generation tools, such as the James Webb Space Telescope, which is capable of peering through cosmic dust and seeing in infrared wavelengths with unprecedented sensitivity. Combined with precision instruments capable of measuring stellar velocities and gravitational effects, there may come a time when the hidden black hole, if it exists, can finally be revealed. Of course, there's a more radical possibility. What if A2261 BCG never had a central supermassive black hole to begin with? This theory upends much of what we think we know about galaxy formation. Conventional wisdom holds that supermassive black holes and galaxies evolve together, a concept called coevolution. The growth of a galaxy's central bulge is closely tied to the mass of its central black hole, a correlation supported by hundreds of observational data points. Yet A2261 BCG may represent an outlier, a relic from an earlier epoch of the universe where different rules applied. Perhaps its core was shaped by dark matter dynamics, or by feedback from an unusually active period of star formation, or by exotic forms of matter or energy we don't yet understand. In this view, the missing black hole isn't an anomaly. It's a clue that our model of galaxy formation is incomplete, and that the story of cosmic structure is far more diverse than we once believed. Astronomers are also exploring the role of dark matter in A2261 BCG's evolution. This invisible, yet dominant component of the universe exerts gravitational forces that shape galaxies, clusters, and cosmic filaments. It's possible that A2261 BCG's massive core and missing black hole are connected to an unusual distribution of dark matter, perhaps a massive dark matter halo offsetting the gravitational need for a central black hole, or altering stellar motion in a way that masks its presence. Still, these ideas remain speculative. What we know for certain is that A2261 BCG, located approximately 3 billion light-years away in the Abell 2261 galaxy cluster, defies expectations. It is the largest and most massive galaxy in its cluster, with a size of over 1 million light-years, 10 times the diameter of the Milky Way. Its central core is the largest ever measured, spanning over 10,000 light-years. And yet, despite this grandeur, it lacks the one feature that should anchor its core, the supermassive black hole. This paradox has captivated astronomers since the core was first imaged by the Hubble Space Telescope. Over the years, Chandra X-ray Observatory, the Very Large Array, VLA, and other instruments have scoured the region for signs of black hole activity. Each null result only deepens the mystery, as we continue to seek answers in the silence. The mystery of A2261 BCG's missing black hole is not just a puzzle about one galaxy. It is a test of everything we believe about cosmic evolution. It reminds us that the universe is under no obligation to conform to our theories, and that each anomaly is an opportunity to learn something new. Whether the black hole was kicked out, hidden, or never existed at all, its absence forces us to refine our understanding of black holes, galaxy mergers, gravitational dynamics, and the fundamental architecture of the cosmos. And so, the story continues. Observations are ongoing. Hypotheses are evolving. The tools are getting sharper, the sky darker, and the questions deeper. In the silence of A2261 BCG's core, we are reminded that even emptiness can speak volumes, if only we learn to listen. A2261 BCG is not an isolated case, but rather a focal point in a broader search to understand how galaxies and their central engines, supermassive black holes, form, evolve, and sometimes vanish. Its mystery echoes across cosmological scales, encouraging astronomers to revisit and revise long-standing assumptions. As data accumulates from instruments like JWST, ALMA, and the Vera-C, Rubin Observatory, more galaxies with similar anomalies may come to light. Perhaps A2261 BCG is the first known of many. This raises an unsettling question: could the traditional model, where every massive galaxy houses a supermassive black hole, be an oversimplification? While the black hole bulge mass correlation has been reinforced by decades of research, perhaps it's a rule with notable exceptions. If galaxies can survive, or even thrive, without central black holes, then black holes may not be as central to galactic evolution as we thought. Alternatively, these exceptions might indicate a temporary absence, a transient phase in a dynamic life cycle that spans billions of years. Consider the cosmic timescales involved. Galaxies live for tens of billions of years. If a black hole was ejected from A2261 BCG just a few 100 million years ago, it would still be relatively nearby, astronomically speaking, but undetectable by current technology. Alternatively, the galaxy might be in a dormant phase, its central black hole present but starved of fuel and thus effectively invisible. This dormancy could last billions of years, making the black hole all but undetectable until some event, like a gas cloud falling inward or a stellar collision, reignites activity. Another line of thought explores the possibility that the missing black hole is not merely invisible, but has undergone some transformation that changes its observable characteristics. Speculative theories have proposed dark, black holes, objects that no longer interact with their environment in familiar ways. If quantum gravity effects or exotic matter states are involved, the black hole might not behave as expected. These ideas remain highly theoretical, but A2261 BCG's emptiness lends credence to the need for new physics. The observational challenges in studying such galaxies are profound. Even at 3 billion light-years away, the level of detail we can resolve is limited. Most of what we infer comes from the behavior of stars and gas, from subtle shifts in light, from faint X-ray emissions, and from the gravitational tug on surrounding objects. It's akin to trying to understand a machine by watching how it shakes a table in a dark room. The absence of a black hole in the data doesn't prove it's not there. It may simply be operating in a regime we don't yet understand. What makes A2261 BCG especially intriguing is that its central region is not just missing a black hole, it also exhibits other signs of disturbance. The stars in its core move in unusual ways, with lower velocities than expected, suggesting that the gravitational well at the center is shallower than it should be. There are also subtle asymmetries in the star distribution, which may be relics of a violent past. Perhaps the ejection event, if it occurred, left behind ripples in the stellar structure like the wake of a ship. Efforts to simulate such events using high-performance computing have begun to bear fruit. Cosmological simulations that include black hole mergers and gravitational recall are being tested against galaxies like A2261 BCG. In some of these virtual universes, black holes are indeed kicked out, and the host galaxies evolve with hollowed cores, flattened velocity profiles, and faint stellar companions trailing behind the ejected black hole. These simulations help bridge theory and observation, providing a sandbox where ideas can be tested at scales no laboratory could ever replicate. There's also a human dimension to this mystery. A2261 BCG is a reminder of how science advances, not in a straight line, but through puzzles, paradoxes, and the courage to question fundamentals. Each attempt to explain the missing black hole pushes the boundaries of what we know. It inspires engineers to build more sensitive instruments, theorists to imagine bolder ideas, and observers to comb the skies more carefully. One can't help but wonder, what if we find more galaxies like this? What if A2261 BCG isn't rare, but the first data point in a new class of galactic behavior? If so, our entire understanding of how galaxies assemble, evolve, and connect with black holes may need to be rewritten. Perhaps there are galaxies that routinely lose their central black holes. Perhaps the universe has been scattering them into the void for billions of years. If so, there could be thousands, millions, of rogue supermassive black holes silently drifting between galaxies, invisible unless they happen to pass through gas clouds or interact gravitationally with other matter. This scenario is more than poetic. It's testable. If future surveys detect compact sources moving independently through intergalactic space, sources with unusually high stellar densities and velocity dispersions, they might be the exiled hearts of galaxies, still carrying the scars of their origin. In the years ahead, the search will intensify. Telescopes will scan deeper. Simulations will grow more sophisticated. And A2261 BCG will remain a key touchstone, a cosmic ghost story whispered across billions of light years, daring us to listen more closely, to look more deeply, and to imagine more freely. The truth, as always in science, may turn out to be stranger than we dared believe. The strangeness of A2261 BCG continues to ripple through the astronomical community not only for what it lacks but for what it could teach us about the very building blocks of cosmic architecture. Galaxies, as we understand them, are not just accumulations of stars, gas, dust, and dark matter. They are structured ecosystems with dynamics largely governed by their central regions. At the heart of most large galaxies lies a supermassive black hole, a gravitational behemoth that anchors the swirling disk of stars around it, shaping orbits, influencing growth, and in many cases, controlling star formation itself through powerful feedback mechanisms. The absence of such a black hole in A2261 BCG is not merely a curiosity, it's an anomaly that defies an entire paradigm. But let's not be too quick to assume we've reached the final conclusion on its absence. It may be hidden in plain sight. The observational limits of our current instruments, especially when peering across distances of billions of light years, constrain our ability to resolve structures on the smallest scales. Even the Hubble Space Telescope, with its exquisite resolution, cannot definitively confirm or deny the presence of a dormant, an active black hole at the galactic core unless that black hole happens to betray itself through some dynamic signature, like swallowing a nearby star or emitting detectable radiation. If such events aren't occurring, the central object could lurk unseen, a cosmic phantom nestled in the heart of a luminous giant. One method astronomers use to infer the presence of a black hole is through stellar velocity dispersion, the spread and speeds of stars orbiting the center of a galaxy. Normally, a black hole adds a significant gravitational pull that accelerates the stars nearby. In A2261 BCG, however, the velocities in the core are strangely low. Instead of speeding up, the stars appear to be almost meandering, as if nothing heavy is drawing them inward. It's a strange signature, inconsistent with expectations, and yet not entirely definitive. There could be mass there, but distributed more diffusely than a singular black hole would allow. Let's go deeper into the concept of core scouring. During galaxy mergers, the supermassive black holes of the two galaxies eventually spiral into each other due to the emission of gravitational waves, and in the process, they scatter stars out of the core, creating a chord profile, a depleted region where stellar density drops. A2261 BCG has one of the largest cores ever observed in any galaxy, nearly 10,000 light-years across, and this is consistent with a past that included massive black hole activity. But where is that black hole now? If the binary did merge, then perhaps, as some models predict, the merged black hole received a powerful gravitational wave recoil, essentially a cosmic kick, that hurled it out of the galactic center. How powerful would that kick need to be? Gravitational wave simulations suggest that recoil velocities can reach up to 5,000 km per second in extreme conditions, depending on the spin, mass ratio, and alignment of the merging black holes. For a black hole to escape a massive galaxy like A2261 BCG, it would need to exceed the galaxy's escape velocity, which is no trivial feat, but if it didn't quite escape, It might still be roaming within the galaxy's outer halo, oscillating back and forth through its gravitational potential well, leaving detectable footprints in the form of displaced light or high-velocity stars. And here's where the search grows more intense. Astronomers have turned to radio telescopes, X-ray observatories, and high-resolution optical instruments to scan the vicinity of A2261 BCG for any signs of such a rogue black hole. In 2012, observations from the Chandra X-ray Observatory failed to detect any X-ray emissions from the galactic center, which again argues against an active nucleus. Still, there are candidate locations, off-center regions with peculiar concentrations of stars, that could be harboring a recoiled black hole enveloped by a tight cluster of bound stars. These compact star clusters are sometimes called hypercompact stellar systems, and could be the trailing remnants of a black hole that once ruled the center. Imagine such a system, a black hole wandering the galaxy's outskirts, dragging with it thousands or even millions of stars, locked in tight orbits. From afar, it would appear as a faint, fast-moving smudge of light, distinguishable only with the most precise observations. Detecting such an object requires careful mapping of stellar velocities, proper motions, and perhaps gravitational lensing effects. No such object has yet been definitively identified in A2261 BCG, but the hunt continues. Now, let's stretch our minds further. What if the black hole didn't just leave the galaxy but was somehow destroyed or transformed? While general relativity insists that black holes are indestructible once formed, quantum gravity theories suggest stranger possibilities. In some hypotheses, black holes could evaporate via Hawking radiation, though on timescales far longer than the age of the universe. Other ideas propose phase transitions in spacetime that could collapse or disrupt a black hole, turning it into something else, a remnant object that interacts weakly with the observable universe. These ideas remain speculative, but in the face of observational mysteries like A2261 BCG, they gain new relevance. The galaxy itself is an extraordinary object even beyond its missing nucleus. With a diameter exceeding 1 million light-years, it is one of the largest known galaxies in the universe. It resides at the heart of the galaxy cluster Abell 2261, a massive structure of hundreds of galaxies bound together by gravity and embedded in a dark matter halo. Brightest cluster galaxies, BCGs, like A2261 BCG, are typically the most massive galaxies in the universe, having grown through the successive mergers of smaller galaxies over billions of years. They often host enormous black holes, some among the most massive ever measured, exceeding 10 billion solar masses. This makes the lack of such a black hole in A2261 BCG all the more bizarre. In this context, the core of A2261 BCG might be seen as a fossil, a remnant of a dramatic event in the galaxy's past. If the black hole was ejected in a gravitational wave recoil, then this galaxy serves as a cosmic time capsule, preserving the aftermath of a black hole merger billions of years ago. It is as though we are witnessing the echo of an invisible catastrophe, with the structure of the galaxy holding clues like fingerprints at a crime scene. Every ripple in star density, every offset in light, every subtle anomaly could tell a piece of the story. Gravitational waves themselves might one day provide the final piece of this puzzle. The Laser Interferometer Space Antenna, LISA, a future European Space Agency mission, is designed to detect low-frequency gravitational waves emitted by supermassive black hole mergers. If operational in the coming decades, LISA might catch such events in real time, allowing astronomers to connect them with galaxies like A2261 BCG. Perhaps one day, we'll even detect a rogue black hole through its gravitational effects alone, without any light at all, a ghost revealed by the very fabric of spacetime trembling in its wake. Until then, A2261 BCG remains an enduring enigma. It stands as a testament to the limits of our understanding and a beacon for scientific curiosity. The deeper we look, the stranger it becomes. And in that strangeness lies the thrill of discovery. For every answer it withholds, it beckons us closer, inviting us to probe, to theorize, and to wonder. The mystery of A2261 BCG's missing central black hole compels us to re-examine the very processes that govern galaxy formation and evolution. Conventional models have long held that supermassive black holes and their host galaxies co-evolve through a delicate feedback mechanism. As gas falls into the black hole, it triggers energetic outflows and radiation, which regulates star formation and shape the galactic environment. Without this central engine, how has A2261 BCG maintained its enormous mass and sprawling stellar population? The answer lies in piecing together the subtle clues left by its structure and dynamics. The unusual flatness and size of A2261 BCG's core challenge astronomers to explore the mechanisms by which stellar orbits are disrupted or rearranged. In most elliptical galaxies, stars near the center crowd densely around the black hole, their orbits tightly bound by the immense gravitational pull. But in A2261 BCG, the central region appears unusually diffuse. One possibility is that a trio of black holes once inhabited the core. If a third black hole merged into a binary, it could have caused a complex gravitational dance, violently ejecting stars and black holes alike from the center. This so-called three-body interaction is a chaotic but well-studied gravitational phenomenon that can produce high-velocity black hole recoils. Another angle to explore is the role of dark matter in shaping the galaxy's core. While dark matter is invisible, it contributes the majority of mass in galaxy clusters. It forms large halos that extend far beyond the visible matter and can dominate the gravitational potential on large scales. If the dark matter density profile within A2261 BCG's core deviates significantly from predictions, due perhaps to past interactions or mergers, it could explain the unusual stellar distribution. A less dense dark matter crust would weaken the gravitational grip at the center, allowing stars to drift apart and creating a larger, flatter core. To probe this, astronomers utilize gravitational lensing, a phenomenon predicted by Einstein's general relativity, where massive objects bend the path of light from background sources. By studying how A2261 BCG distorts the images of more distant galaxies, researchers can map its mass distribution with high precision. Early lensing studies indicate that while the dark matter halo is massive, its inner profile may be less steep than expected, supporting the hypothesis that the core's structure is influenced by a combination of black hole dynamics and dark matter configuration. Moreover, the chemical composition and age of stars in the core offer another window into the galaxy's history. Spectroscopic studies have revealed that the stars in the core of A2261 BCG are predominantly old and metal-rich. This implies a complex and violent history of star formation and galactic cannibalism. As smaller galaxies merged into A2261 BCG over billions of years, their stars were absorbed and redistributed. Each merger event could have contributed to core scouring, black hole mergers, and subsequent black hole ejections, gradually shaping the enormous low-density core we observe today. Intriguingly, the lack of an active black hole nucleus raises questions about the galaxy's future evolution. Typically, accretion of matter onto a central black hole powers quasars and active galactic nuclei, AGN, which influence star formation rates by heating and expelling gas. In A2261 BCG, without such a nucleus, star formation may proceed unchecked or conversely may have shut down due to the depletion of gas over time. Observations suggest the latter. The galaxy exhibits low levels of current star formation, consistent with the idea that it is a red and dead elliptical, having exhausted its star-forming fuel long ago. Yet, the mystery deepens when considering that A2261 BCG resides in a rich cluster environment, where interactions with intracluster gas and smaller satellite galaxies could replenish cold gas. Why then has this galaxy not rejuvenated its star formation? One hypothesis involves the presence of a distributed network of smaller black holes or massive compact objects in the core region. These could inject energy into the gas, preventing it from cooling and collapsing into new stars, mimicking the effect of a central supermassive black hole but on a more subtle scale. The technological challenges of studying A2261 BCG are immense. Situated nearly 3 billion light-years away, its light has traveled across vast expanses of space and time. This means that our observations capture the galaxy as it existed billions of years ago, not as it is today. The delay, a consequence of the finite speed of light, means astronomers are studying a snapshot frozen in cosmic history. To understand its present state, we must infer its evolutionary trajectory from models and analogies with closer galaxies. Future observatories promise to transform our understanding of A2261 BCG. The James Webb Space Telescope, JWST, with its unprecedented infrared sensitivity and resolution, can peer through dust and detect faint signatures of accretion or star formation. Likewise, next-generation X-ray observatories will hunt for the faintest traces of black hole activity. Ground-based extremely large telescopes, equipped with adaptive optics, will dissect stellar motions in exquisite detail, searching for the gravitational imprint of unseen massive objects. On a theoretical front, advances in computational astrophysics are enabling simulations that incorporate the complex interplay of gravity, gas dynamics, black hole physics, and dark matter on galactic scales. Simulating a galaxy as massive and as uniquely structured as A2261 BCG pushes these models to their limits. Each simulation iteration refines our understanding, exploring scenarios like black hole mergers, gravitational wave recoil, and stellar redistribution. Such simulations help astronomers generate predictions that can be tested by observations, forming a feedback loop between theory and data. The implications of understanding A2261 BCG extend beyond this single galaxy. If supermassive black holes can be ejected from their host galaxies or become effectively invisible, this challenges many assumptions in cosmology and galaxy evolution. It raises questions about the growth of structure in the universe, the formation of quasars, and the demographics of black holes across cosmic time. The existence of galaxies without central black holes, or with off-center ones, could affect models of gravitational wave backgrounds, as well as interpretations of cosmic X-ray and radio surveys. In a philosophical sense, A2261 BCG teaches us humility in our quest to comprehend the cosmos. It exemplifies how the universe continually surprises us, revealing exceptions that shake our confidence in prevailing paradigms. It urges us to keep searching, to question, and to refine. This colossal galaxy, with its ghostly core and missing heart, stands as both a puzzle and a beacon, a reminder that even the grandest cosmic edifices harbor secrets still waiting to be unraveled. As we continue to study A2261 BCG, new technologies, theoretical breakthroughs, and innovative observational strategies will bring us closer to unraveling its mysteries. Whether its central black hole remains forever hidden, has been ejected into intergalactic space, or has transformed in ways we cannot yet comprehend, its story will deepen our understanding of the universe's most powerful phenomena. The journey to uncover the truth about A2261 BCG is far from over. It is an unfolding saga of cosmic discovery that will inspire astronomers and dreamers for generations to come. Delving deeper into the enigma of A2261 BCG's missing central black hole requires us to consider the broader cosmic context in which this galaxy exists. It resides within the Abell 2261 galaxy cluster, a massive assembly of hundreds of galaxies bound together by gravity. The environment of galaxy clusters is extraordinarily dynamic. Galaxies frequently interact and merge, their gravitational fields influencing one another, causing tidal distortions and sometimes violent collisions. Such interactions contribute significantly to the evolution of galaxies within clusters, including the formation of the colossal brightest cluster galaxies, BCGs, like A2261 BCG. Brightest cluster galaxies often occupy the gravitational center of their clusters and are typically the most massive and luminous galaxies in the universe. They grow by cannibalizing smaller galaxies and accumulating gas and dark matter. Given this history, the core structure of A2261 BCG, so unusual and flat, is particularly puzzling because it suggests a process that went beyond normal galaxy mergers and accretions. One of the most compelling theories to explain the missing black hole involves the physics of black hole mergers and the emission of gravitational waves. When two supermassive black holes spiral together and merge, they release vast amounts of energy in gravitational waves, ripples in the fabric of spacetime. If the gravitational wave emission is asymmetric, it can impart a kick to the newly formed black hole, potentially ejecting it from the galaxy's core at speeds up to thousands of kilometers per second. This gravitational wave recoil could explain the absence of a central supermassive black hole in A2261 BCG. After a series of galaxy mergers, two black holes might have merged, only to be violently propelled away from the center. If this event occurred billions of years ago, the black hole might now be wandering the outskirts of the galaxy, or even completely escaped into intergalactic space. Observationally, confirming this scenario is extremely challenging. Detecting a supermassive black hole without its bright accretion disk requires indirect methods, such as looking for the influence of its gravity on surrounding stars or gas. Some efforts have focused on searching for offset active galactic nuclei or hypercompact stellar systems that might accompany a recoiling black hole. In the case of A2261 BCG, no clear evidence has yet emerged to definitively pinpoint the black hole's whereabouts. The concept of a supermassive black hole wandering through intergalactic space might sound like science fiction, but it is grounded in solid theoretical physics. A black hole ejected at high velocity could traverse hundreds of thousands of light-years over millions of years. Such a rogue black hole might carry with it a small cluster of tightly bound stars, making it a faint, fast-moving object against the cosmic backdrop. Apart from gravitational wave recoil, another intriguing possibility involves the existence of a binary or multiple black hole system within A2261 BCG. Rather than a single supermassive black hole, the core might host two or more black holes orbiting each other at subparsec scales. These systems are expected to be common after galaxy mergers but are notoriously difficult to detect due to their compactness and the absence of strong accretion signatures. If A2261 BCG contains a binary supermassive black hole system, their gravitational interactions could heat the stellar core, causing the stars to migrate outward and create the large, flat core observed. This scouring effect has been predicted by simulations and may offer an explanation for the galaxy's diffuse center without requiring the black hole to be missing entirely. Expanding the scope, the discovery of galaxies like A2261 BCG challenges the long-held paradigm that every massive galaxy must host a central supermassive black hole. It forces astrophysicists to reconsider how ubiquitous these black holes are and how their growth and interactions shape galaxies. If some galaxies can survive or evolve without a central black hole, what does that mean for the feedback mechanisms that regulate star formation and galactic evolution? Furthermore, it opens the door to the idea that our census of supermassive black holes may be incomplete. There could be populations of off-center or ejected black holes that remain hidden to current observational methods. Detecting these elusive objects would require new instruments, techniques, and creative approaches, such as searching for gravitational wave signals, radio emissions, or the subtle motion of stars influenced by unseen masses. Another area of investigation lies in the relationship between the galaxy's stellar population and the central core properties. The stars in A2261 BCG's core show an unusual distribution, with a core radius much larger than expected for a galaxy of its size. This suggests that some dynamic process has removed or redistributed stars near the center. Detailed spectroscopic studies reveal that these stars have a high metallicity, indicating that they formed in an environment rich in heavy elements and that the galaxy has undergone intense periods of star formation in the past. The age distribution of stars offers clues about the timing of mergers and black hole interactions. If a black hole was ejected relatively recently in cosmic terms, one might expect to see signatures of disturbance in the stellar motions or the presence of younger stars formed from gas disturbed during the event. So far, observations suggest a relatively quiescent recent history, implying that any dramatic black hole ejection likely occurred in the distant past. Looking forward, the field of gravitational wave astronomy holds great promise for shedding light on these mysteries. The Laser Interferometer Space Antenna, LISA, a planned space-based gravitational wave detector, will be capable of detecting the mergers of supermassive black holes with unparalleled sensitivity. It may directly observe the final in spiral and merger events that could lead to black hole recoil. Combining gravitational wave data with electromagnetic observations will enable astronomers to link dynamic black hole activity with observable galactic features like cores and star distributions. Additionally, the search for off-nuclear active galactic nuclei using next-generation telescopes could reveal displaced black holes or systems on the move. High-resolution X-ray and radio surveys may uncover faint accretion signatures that betray the presence of wandering supermassive black holes. The mysteries surrounding A2261 BCG also intersect with broader questions about dark matter. While dark matter is a cornerstone of cosmological models, its detailed distribution and interaction with baryonic matter, normal matter, remain elusive. The core of A2261 BCG offers a natural laboratory for testing how dark matter behaves under extreme conditions and whether it influences the dynamics of black holes and stars in unexpected ways. Some alternative theories propose that modifications to gravity, or exotic forms of dark matter could produce the observed core structures without invoking missing black holes. While these ideas remain speculative, they underscore the importance of using diverse approaches to understand such complex systems. Ultimately, the saga of A2261 BCG exemplifies the dynamic, evolving nature of astrophysics. Each new observation, simulation, or theoretical insight reshapes our understanding, revealing the universe as a vast, interconnected web of phenomena, often stranger than fiction. As technology advances and collaboration across disciplines grows, the secrets of this giant galaxy and its mysteriously missing central black hole will come into sharper focus, guiding us toward a deeper comprehension of the cosmos. The story of A2261 BCG invites us to explore the fundamental processes that govern galaxy formation and evolution on the grandest scales. As the largest known galaxies, brightest cluster galaxies like A2261 BCG are cosmic behemoths that have assembled over billions of years through a series of mergers and accretions. These mergers not only build up the galaxy's mass but also profoundly influence its core structure and central black hole dynamics. One key insight into this process comes from detailed computer simulations of galaxy mergers. These simulations model the gravitational interactions of stars, gas, dark matter, and black holes over cosmic timescales. They predict that when two galaxies merge, their central black holes sink toward the new combined galaxy center due to dynamical friction, eventually forming a binary system. This binary black hole then hardens, ejecting stars from the core region through gravitational slingshot effects, which scours out a large, diffuse stellar core. This phenomenon matches the large, flat core observed in A2261 BCG and similar galaxies. However, the simulations also show that if the two black holes eventually merge, the newly formed black hole can receive a powerful recoil kick due to the anisotropic emission of gravitational waves. Depending on the magnitude of this kick, the black hole may oscillate within the galaxy's core or be completely ejected from the galaxy. The probability of ejection depends on factors such as the mass ratio and spin orientations of the merging black holes. The absence of a detectable supermassive black hole at the center of A2261 BCG aligns well with this scenario of gravitational wave recoil. If the black hole was ejected, the galaxy would be left with a core depleted of stars due to the binary scouring before the merger. Over time, the stellar distribution would relax into the observed large, flat core. The recoiling black hole might still be nearby, traveling through the galaxy or cluster, but its detection is extremely challenging without luminous accretion signatures. Scientists have also considered whether A2261 BCG might contain a dormant, or quiescent black hole, one not currently accreting enough matter to shine brightly in X-rays or other wavelengths. Even a quiescent black hole exerts gravitational influence, which can be detected by measuring the velocities of stars near the core. Precise measurements using advanced instruments like the Hubble Space Telescope and ground-based adaptive optics systems have failed to find the expected stellar velocity increase near the center that would indicate a supermassive black hole's presence. This null result is striking and further supports the idea that the black hole may be missing or displaced. Alternative hypotheses include the possibility that the black hole is unusually small or off-center, or that the core is dominated by other dark compact objects. Yet none of these alternatives fit the data as well as the black hole ejection scenario. Exploring the implications of a missing central black hole leads us to reconsider the role such black holes play in galaxy evolution. Supermassive black holes are believed to regulate star formation and gas dynamics through feedback mechanisms, energetic outflows and radiation that heat or expel gas, preventing runaway star formation. Without a central black hole, these regulatory processes may be absent or altered, potentially influencing the galaxy's future development. Moreover, the missing black hole raises questions about the fate of the ejected black hole itself. As a supermassive black hole expelled from its host, it would travel through the galaxy cluster's environment, interacting gravitationally with other galaxies, dark matter halos, and intergalactic gas. Such rogue black holes might be common but virtually invisible, detectable only through indirect signatures such as gravitational lensing effects or rare accretion events. The search for ejected supermassive black holes is an emerging field of astrophysical research, driven by the advent of gravitational wave astronomy and advanced observational techniques. Upcoming observatories like the James Webb Space Telescope and next-generation X-ray telescopes will provide unprecedented sensitivity to faint black hole signatures, while gravitational wave detectors like LISA will open new windows onto black hole mergers. In addition to its astrophysical mysteries, A2261 BCG provides a natural laboratory to study the interplay between baryonic matter, stars and gas, and dark matter, the unseen mass that dominates the universe's gravitational landscape. The large core and the absence of a central black hole challenge standard models of dark matter distribution and galaxy formation. Some researchers propose that interactions between dark matter and baryons during mergers could contribute to the core's expansion and flattening. Others suggest that phenomena such as self-interacting dark matter, a hypothetical form of dark matter that scatters off itself, might explain the core structure by creating a central core in the dark matter halo rather than the steep, cuspy profiles predicted by standard cold dark matter models. Studying A2261 BCG in detail could thus help constrain dark matter properties and improve cosmological models. Another fascinating aspect of A2261 BCG is the implication for the growth and evolution of supermassive black holes themselves. If gravitational wave recoil frequently ejects merged black holes, then the growth of the most massive black holes may be limited or episodic, depending on the frequency of ejection events and the ability of galaxies to recapture wandering black holes. This scenario could affect our understanding of the correlations observed between black hole mass and properties of their host galaxies, such as the bulge mass or stellar velocity dispersion, known as the M-sigma relation. If black holes are sometimes missing or displaced, these relations might be more complex than previously thought, reflecting a dynamic cosmic dance between galaxies and their central black holes. From a technological perspective, probing the mysteries of A2261 BCG drives innovation in instrumentation, data analysis, and theoretical modeling. Techniques such as integral field spectroscopy, which maps the motions of stars and gas in 2 dimensions, and high-resolution imaging enable astronomers to dissect galaxy cores with unprecedented detail. Simultaneously, advances in computational astrophysics allow for increasingly realistic simulations of galaxy mergers and black hole dynamics. These interdisciplinary efforts not only seek to solve the puzzle of A2261 BCG, but also enrich our broader comprehension of the universe. They exemplify the synergy between observation, theory, and technology that propels modern astrophysics. The giant galaxy A2261 BCG with its mysteriously missing central black hole stands as a cosmic enigma that challenges fundamental assumptions about galaxies and their black holes. Its large, diffuse core, absence of a detectable supermassive black hole, and the potential presence of an ejected black hole highlight the complex and dynamic processes that shape the universe on its grandest scales. As our observational capabilities and theoretical understanding continue to advance, A2261 BCG remains a compelling target for unraveling the intricate interplay between gravity, matter, and space-time, offering profound insights into the nature of galaxies, black holes, and the cosmos itself. Delving deeper into the mystery of A2261 BCG, it is essential to understand the observational techniques that astronomers have employed to study this colossal galaxy and its core. The initial detection and detailed imaging of A2261 BCG's core came from the Hubble Space Telescope's advanced camera for surveys. This instrument allowed astronomers to observe the galaxy at unprecedented resolutions, revealing its unusually large and nearly flat core, a characteristic far different from the sharp, dense cores typically seen in massive elliptical galaxies. The flatness of the core means there is a significant deficit of stars near the center compared to what would be expected from a standard stellar distribution. This observation immediately hints at a past event or process that removed stars from the central region. Typically, in other massive galaxies, the gravitational influence of a supermassive black hole creates a dense stellar cusp due to its powerful pull. The absence of such a cusp in A2261 BCG strongly suggests that some mechanism has evacuated stars from the center. To confirm whether a supermassive black hole resides at the center, astronomers use a variety of indirect methods. One common approach is to measure the motions of stars in the core. The gravitational pull of a supermassive black hole causes stars to move faster near the center. By carefully measuring the Doppler shifts in the spectra of stars near the core, astronomers can infer the black hole's presence and estimate its mass. These observations were carried out using the Hubble Space Telescope and large ground-based telescopes equipped with adaptive optics, such as the Keck Observatory in Hawaii. Surprisingly, these measurements did not reveal the expected increase in stellar velocity dispersion that would indicate a central black hole with a mass predicted by the galaxy's luminosity and mass. The black hole, if present, would have to be significantly smaller than expected or located away from the center, either of which aligns well with observations. Furthermore, X-ray observations using the Chandra X-ray Observatory, designed to detect high-energy emissions from accretion disks around supermassive black holes, also failed to detect any significant signal from the galaxy's center. This lack of X-ray emission reinforces the idea that either the black hole is absent, not actively accreting material, or hidden in some unusual way. Another critical aspect of studying A2261 BCG involves exploring the possibility of the black hole being displaced from the core. If the black hole received a recoil kick during a merger event, it could be oscillating within the galaxy or wandering in the outskirts. To search for such a wandering black hole, astronomers look for unusual sources of emission, such as compact radio sources or off-center X-ray emissions, that might signify the black hole's location. Despite extensive surveys across multiple wavelengths, radio, optical, infrared, and X-ray, no convincing evidence has emerged to pinpoint a displaced black hole. This absence raises fascinating questions about how far the black hole might have traveled, how it interacts with the galaxy's environment, and how long such a black hole could remain undetected. Theoretical models provide some answers, suggesting that a supermassive black hole ejected with a sufficiently high velocity could escape the gravitational pull of its host galaxy entirely and become a rogue black hole, drifting through intergalactic space. Alternatively, if the recoil velocity is smaller, the black hole may oscillate back and forth through the galaxy core over millions to billions of years, gradually settling back to the center due to dynamical friction with stars and dark matter. The time scales and dynamics of these processes depend on many factors, including the mass of the black hole, the density and distribution of stars and dark matter in the core, and the initial velocity imparted by the gravitational wave recoil. These complex interactions are the subject of ongoing research using high-resolution N-body simulations and hydrodynamic models. Beyond the immediate black hole mystery, the properties of A2261 BCG provide a window into the environment of galaxy clusters. A 2261 BCG resides in the Abell 2261 galaxy cluster, a massive conglomerate of hundreds of galaxies bound together by gravity. Galaxy clusters themselves are fascinating cosmic structures, serving as laboratories for studying dark matter, galaxy evolution, and the large-scale structure of the universe. Within such a dense environment, galaxies frequently interact and merge, contributing to the growth of brightest cluster galaxies like A2261 BCG. These repeated mergers over billions of years lead to complex dynamical histories, reflected in the structural properties observed today. The extended halo of stars surrounding A2261 BCG and its massive size point to a long history of such mergers. Moreover, the intracluster medium, a hot, diffuse plasma that fills the space between galaxies and clusters, influences galaxy evolution by stripping gas from galaxies and regulating star formation. Understanding how A2261 BCG interacts with this medium sheds light on the broader processes governing galaxy clusters. An intriguing question arises about how the absence of a central black hole might affect the galaxy's future evolution. Supermassive black holes are thought to play a critical role in regulating star formation through active galactic nucleus (AGN) feedback. When material falls onto a supermassive black hole, it releases enormous amounts of energy, heating surrounding gas and sometimes driving powerful outflows that prevent the gas from cooling and collapsing into new stars. Without such a feedback mechanism, A2261 BCG might be expected to experience different star formation rates compared to other brightest cluster galaxies with active black holes. Observations of its stellar population and gas content over time could help clarify this effect, offering insights into the interconnected roles of black holes and galaxy evolution. Additionally, the missing black hole problem in A2261 BCG connects to broader questions about gravitational wave physics. The kick velocities necessary to eject supermassive black holes arise from anisotropic gravitational wave emission during black hole mergers, a prediction of general relativity that has profound implications for astrophysics. Detecting and studying such kicks helps verify gravitational wave theory and informs predictions for gravitational wave observatories. As gravitational wave detectors like LIGO and Virgo continue to observe stellar mass black hole mergers, future space-based observatories like LISA, Laser Interferometer Space Antenna, will be capable of detecting waves from merging supermassive black holes. These observations may provide direct evidence of recoil kicks and their astrophysical consequences, including the phenomenon observed in A2261 BCG. On a more speculative front, the mystery of A2261 BCG invites us to ponder the nature of black holes themselves. Could there be exotic alternatives to supermassive black holes lurking in galaxy centers? Concepts like boson stars or other hypothetical compact objects arise in some theoretical models, though they remain highly speculative. Such alternatives would have very different observational signatures and could potentially explain anomalies like the missing black hole in A2261 BCG if supported by future evidence. A2261 BCG serves as a remarkable cosmic case study, intertwining themes of galaxy formation, black hole physics, gravitational waves, and dark matter. The ongoing quest to understand its missing central black hole pushes the frontiers of astronomy, physics, and cosmology, highlighting the dynamic and evolving nature of the universe. The enigma of A2261 BCG's missing central black hole does more than simply pose a fascinating astrophysical puzzle. It shakes the foundations of several well-established cosmological models and assumptions. The standard narrative of galaxy formation suggests a near-universal correlation between the mass of a galaxy and the mass of the supermassive black hole at its center. This empirical relation, known as the M-sigma relation, has been repeatedly observed in countless galaxies. The larger the stellar bulge, the more massive the central black hole. Yet, here in A2261 BCG, a galaxy among the most massive ever discovered, the expected centerpiece is conspicuously absent. This anomaly compels researchers to revisit how supermassive black holes come to reside in galactic centers to begin with. In early cosmic history, primordial black holes formed from the collapse of massive stars and possibly even from density fluctuations in the early universe. These seeds would have accreted matter and merged with other black holes over time, growing in size. As galaxies collided and coalesced, their central black holes were expected to follow, ultimately merging due to dynamical friction and gravitational wave emission. This process is thought to contribute to the tightly bound core and concentrated stellar distribution at the center of galaxies. However, if this process unfolded as expected in A2261 BCG, its black hole should be among the most massive known, perhaps exceeding 10 billion solar masses. Its invisibility, then, becomes even more perplexing. Could it be that A2261 BCG once possessed such a monstrous black hole, only to have it expelled by an extraordinarily violent gravitational event? And if so, what evidence might support or refute such a dramatic scenario? Researchers have proposed that following a merger of two massive galaxies, their central black holes formed a binary and eventually spiraled inward to coalesce. During this final merger, gravitational waves emitted anisotropically could have propelled the newly formed single black hole away from the core with recoil velocities as high as several thousand kilometers per second, enough to launch it completely out of the galaxy or into a wide orbit. This process, known as a gravitational wave recoil or black hole kick, was predicted by numerical relativity simulations and has gained increasing attention in recent years. The core of A2261 BCG, with its huge radius and relatively flat brightness profile, appears consistent with what one might expect from a scoured-out region, a stellar graveyard left behind after a binary black hole displaced stars from the center during its spiral and then recoiled after merging. This offers one of the most compelling explanations for the galaxy's anomalous structure. In fact, simulations of galaxy mergers that include binary supermassive black holes show that stellar cores can be carved out to enormous sizes if the black holes are massive enough. The gravitational slingshot effect flings stars outward as the black hole pair interacts with the stellar environment, leaving behind a puffed-up, underdense core. The moment a merged black hole recoils or exits the nucleus entirely, the central stellar density drops precipitously. Still, for a supermassive black hole to escape from a galaxy as massive as A2261 BCG, the kick would have to be immense. Only under specific conditions, such as a merger between black holes with particular spin orientations and mass ratios, would the resulting gravitational wave emission be lopsided enough to impart such a forceful kick. The rarity of such conditions may explain why A2261 BCG remains a unique case among hundreds of observed massive galaxies. But the lack of direct evidence for a recoiling black hole prompts other intriguing hypotheses. Could the black hole still exist within the galaxy but be heavily obscured, perhaps embedded in a dense shroud of gas or dust, masking its emissions? While such obscuration might suppress detectable X-rays or radio waves, it would be highly unusual for a black hole of this scale to remain dormant for billions of years. Even the occasional accretion of interstellar material would typically generate detectable signatures. Yet, in A2261 BCG, no such signs have been conclusively observed. Astronomers have looked beyond the galaxy's center for clues, identifying a few off-center compact sources in high-resolution Hubble images. These clumps of stars or potential remnants might represent satellite cores, regions that could have been gravitationally influenced or dragged along with a recoiling black hole. If one of these clumps harbors the missing black hole, it may still emit weak radiation. However, until a clear observational fingerprint, such as strong radio jets or X-ray flares, is detected, the identity of these clumps remains ambiguous. The implications of such a displaced black hole go far beyond A2261 BCG. If supermassive black holes can be ejected from their host galaxies, it may explain certain long-standing mysteries in extragalactic astronomy, such as the occasional discovery of galaxies that, based on their mass and morphology, should have active nuclei but appear to lack them. Furthermore, it suggests that rogue black holes, invisible giants wandering between galaxies, may be far more common than previously thought. Detecting these rogue black holes is no simple task. Unlike stars, black holes emit no light of their own. Only when interacting with matter, such as through accretion, do they reveal their presence. A rogue black hole drifting through intergalactic space would likely be surrounded by very little matter, making it virtually undetectable with current instruments. However, gravitational lensing, the bending of light from background sources by a massive foreground object, offers one possible avenue for detection. A rogue black hole passing in front of a distant quasar, for example, might temporarily distort or magnify its light, offering indirect evidence of the black hole's passage. Another possibility lies in the detection of hypercompact stellar systems, tightly packed clusters of stars that may remain gravitationally bound to a recoiling black hole after its ejection. These stellar systems, moving rapidly and located far from any galactic nucleus, could serve as beacons for tracking down elusive supermassive wanderers. Observational campaigns targeting such systems are currently underway with next-generation telescopes. Meanwhile, numerical simulations continue to model the gravitational interactions involved in black hole mergers, helping to predict the distribution and fate of stars in the aftermath. These simulations not only replicate the kinds of large, diffuse cores seen in galaxies like A2261 BCG, but also help fine-tune our understanding of the timescales over which a recoiled black hole might return to the nucleus, if at all. Interestingly, while A2261 BCG is the most prominent example of a galaxy with a seemingly missing central black hole, it is not alone. A handful of other galaxies exhibit similar, though less extreme, signs of core scouring and weak nuclear activity. As observational techniques become more refined and sensitive, astronomers may identify more candidates, piecing together a broader statistical understanding of black hole ejection events. In the coming years, instruments like the James Webb Space Telescope, JWST, and the Extremely Large Telescope, ELT, promise to provide deeper insight into galactic cores with unprecedented clarity. These telescopes will allow researchers to measure the motions of individual stars in greater detail, search for subtle signatures of hidden black holes, and perhaps even witness the long-predicted aftermath of a gravitational wave recall. Moreover, the eventual launch of space-based gravitational wave detectors like LISA will revolutionize our ability to study supermassive black hole mergers directly. These observatories will detect the gravitational waveforms emitted during the final stages of coalescence, the very signals that, if asymmetric, give rise to the black hole kicks discussed here. By correlating such events with observations of galaxies like A2261 BCG, scientists may finally confirm whether gravitational wave recoil is truly responsible for the missing black hole. Thus, A2261 BCG stands not only as an observational anomaly but as a cosmic lighthouse, guiding the future of black hole astrophysics, gravitational wave astronomy, and our understanding of the violent processes that shape the universe. As investigations into A2261 BCG deepen, another possibility surfaces: that the central black hole may not be missing or recoiled, but instead never fully formed in the way astronomers expect. This challenges some of the foundational assumptions about black hole and galaxy coevolution. Could it be that under extreme conditions in the early universe, a galaxy like A2261 BCG could accumulate such tremendous mass through non-standard means, bypassing the typical requirement of a central supermassive black hole? In this alternative scenario, A2261 BCG may have undergone atypical evolutionary processes. Perhaps it experienced a series of dry mergers between galaxies lacking significant gas. Such interactions would limit black hole growth through accretion and star formation, potentially leaving behind a massive galaxy with a bloated core but no significant central engine. This would still leave the question of core structure and stellar distribution, which remains unusually diffuse, but it introduces the idea that black hole presence is not necessarily guaranteed even in the most massive galaxies. Moreover, simulations show that in galaxies formed through multiple dry mergers, central black holes can be delayed in coalescing or may never merge at all if the resulting binary fails to lose energy efficiently. This is known as the final parsec problem, where a pair of supermassive black holes stalls at a small separation because surrounding stars are no longer available to extract orbital energy. In such cases, the black holes might wander through the core, never forming a dominant central object and never generating the conditions needed for a gravitational wave recall. Alternatively, A2261 BCG could represent a transitional phase, the calm before a black hole merger finally completes. If the central region contains a loosely bound binary black hole system, separated by hundreds or thousands of light years, it could remain undetectable with current instruments. Over cosmic time, dynamical friction and interactions with surrounding stars could slowly draw the pair together, setting the stage for a future merger and possibly a powerful gravitational wave event. This idea gains some traction from the galaxy's structure itself. A 2261 BCG contains not just one nucleus, but multiple bright clumps or stellar knots scattered throughout its core. These may be remnants of previous galactic cores, stalled black hole systems, or satellite galaxies that were absorbed during mergers but never fully coalesced. Some of these knots could be hosting wandering black holes, an exciting prospect if confirmed, and a major piece of the puzzle regarding the galaxy's odd morphology. A 2261 BCG also raises questions about the connection between black holes and galactic feedback mechanisms. In most galaxies, active galactic nuclei (AGN), powered by central black holes, regulate star formation by releasing intense radiation and energetic winds. This feedback keeps galaxies from becoming too massive and helps explain why so many follow the observed scaling relations. Yet in a 2261 BCG, if there is no black hole, or a very weak one, how did the galaxy reach such an enormous size and mass without runaway star formation or collapse? This may suggest that feedback can arise from other processes, such as supernova-driven winds or environmental effects from its position in a galaxy cluster. Alternatively, it might indicate that a 2261 BCG once had a black hole which provided feedback in the past, and only recently lost it through ejection or another catastrophic event. In that case, the galaxy may now be adrift, vulnerable to future instabilities or starbursts due to the lack of a central regulator. There's also the tantalizing possibility that a 2261 BCG harbors an exotic type of central object, something more elusive or poorly understood than a traditional supermassive black hole. Some theorists have speculated about the existence of gravastars, boson stars, or dark matter cores, hypothetical objects that could mimic the gravitational influence of a black hole without an event horizon or radiation signature. If such an object sat at the center of a 2261 BCG, it could explain the lack of emissions and the diffuse stellar core. Though purely speculative, these ideas offer creative alternatives for a galaxy that defies classification. The continued mystery surrounding a 2261 BCG makes it a high-priority target for next-generation observational campaigns. The James Webb Space Telescope, with its infrared sensitivity and unprecedented resolution, could probe deeper into the galaxy's dusty interior, revealing whether faint emissions from a dormant black hole or star cluster are present. Similarly, radio interferometers like the Very Large Array, VLA, and X-ray observatories like Chandra or the upcoming Athena mission may help detect weak jets, flares, or hot gas associated with a hidden compact object. As more data are collected and models refined, a 2261 BCG may eventually offer a definitive answer. Either it once had a black hole that was ejected in a cosmic explosion, or it represents a rare case of a massive galaxy evolving along an entirely different path, one that questions the black hole galaxy connection itself. For now, it remains a cosmic riddle, a silent giant with a hollow heart, challenging what we thought we knew about the most powerful forces in the universe. This silence from a 2261 BCG is almost haunting. In a universe filled with explosive energy, blazing quasars, and the relentless pull of gravity, here lies a galaxy that stands as a paradox, an enormous elliptical colossus, sprawling across intergalactic space, yet missing what we expect to find at its very heart. And this mystery isn't a trivial omission, it upends some of our most fundamental astrophysical assumptions. To fully grasp the weight of this enigma, we must explore the broader context in which it exists. A 2261 BCG is located in the Abell 2261 galaxy cluster, a region dense with galaxies, intergalactic gas, and dark matter. It's not just any galaxy in this cluster, it is the brightest cluster galaxy, or BCG. These types of galaxies are thought to form through a long sequence of mergers and accretions over billions of years, becoming the most massive and luminous members of their galactic communities. Their central positions in galaxy clusters make BCGs crucial testing grounds for theories of hierarchical galaxy formation, black hole feedback, and cosmological structure evolution. And yet, in the case of a 2261 BCG, we see that central paradigm shaken. It behaves as though the cosmic rules were bent in its making, or perhaps rewritten altogether. The immense size of A2261 BCG's core is one of the most glaring clues in this cosmic whodunit. The core spans a diameter of about 10,000 light-years, making it one of the largest galactic cores ever observed. Most galaxies, including the most massive ones, have much smaller and more concentrated stellar bulges. The sheer breadth of this diffuse core suggests that something powerful pushed the stars outward, redistributing them over a wider area. This is not a structure easily formed by chance or by simple gravitational settling, it's an imprint of violent dynamical history. One compelling theory is that of a gravitational recoil event, something that occurs when two supermassive black holes merge. When they do, they release intense gravitational waves, ripples in the fabric of space-time. If the black holes are not perfectly symmetrical in mass or spin, these waves are emitted unevenly, producing a recoil or kick to the newly formed black hole. Under the right conditions, this kick can be strong enough to eject the resulting black hole from the center of its galaxy entirely. This would leave behind a gaping void where the black hole once sat, along with an expanded, diffuse stellar distribution caused by the disruption of the surrounding gravitational balance. Now, consider what this means for A2261 BCG. If its black hole was ejected, the telltale signs might still be visible. The surrounding stars would have been pushed into wider orbits, leading to the observed giant core. Additionally, the black hole itself, assuming it was ejected and is still intact, could still be roaming nearby. It might even be dragging some stars along with it, forming a compact stellar cloak or mini-nucleus that could, with the right instruments, be detected. This possibility has led astronomers to closely study four bright stellar knots located near the galaxy's center. These compact structures might be remnants of satellite galaxies, or they might be potential candidates for the missing black hole's new location. If any of them are harboring a supermassive black hole, even one not currently accreting material, it could be identified through subtle velocity shifts, gravitational lensing effects, or faint emissions in X-ray and radio wavelengths. However, none of the candidate knots have conclusively shown the expected signs of housing a supermassive black hole. Their spectra lack the energetic signatures typical of an active nucleus. And yet, the possibility remains open. If the black hole is dormant, emitting no detectable radiation, it might escape observation with current technology. Meanwhile, we must also consider the core scouring theory, which suggests that black holes, even without being ejected, can carve out large cores through repeated interactions and mergers. When galaxies merge, their central black holes eventually sink to the middle due to dynamical friction. As they form binary systems and spiral inward, they gravitationally slingshot stars away from the center, hollowing out the core. If A2261 BCG experienced multiple such mergers, each involving massive black holes, the cumulative effect could produce the enormous void observed today. Still, the size of A2261 BCG's core is so extreme that even this explanation seems strained. It would require an unusually large number of major mergers in a relatively short cosmic timescale, all without forming a settled central black hole. That's difficult to reconcile with what we know about typical galactic evolution, and it makes this galaxy stand out even more as a cosmic outlier. If A2261 BCG's central black hole really is gone, ejected into the surrounding halo, or perhaps beyond, then we may be looking at one of the few examples of a galaxy decapitated by gravitational waves. That makes it more than a curiosity. It becomes an observational relic of the dynamic, violent processes that shape the universe at the largest scales. From a cosmological perspective, galaxies like A2261 BCG are laboratories that allow us to test our theories about the formation of structure in the universe. If black holes can be ejected from galaxies with such force, then the frequency of these events may help refine models of gravitational wave emissions, merger rates, and even the seeding of black holes in the early universe. Furthermore, the apparent contradiction between the galaxy's extreme mass and its missing nucleus raises questions about the so-called M-sigma relation, a well-established empirical correlation between the mass of a galaxy's central black hole and the velocity dispersion of its bulge. A 2261 BCG should host a supermassive black hole on the order of 10 billion solar masses, according to this relation. If it doesn't, then either it once did and lost it, or the relation has exceptions under certain conditions. This could imply that black holes and galaxies do not always co-evolve in lockstep, challenging one of the most deeply held tenets of modern astrophysics. Such deviations may not be rare but instead overlooked due to observational limitations or selection biases. A 2261 BCG invites us to reassess the assumptions we make about how galaxies grow, how black holes form and interact, and how gravitational energy is redistributed across cosmic structures. It's more than a missing object, it's a clue, a challenge, and perhaps even a doorway into physics that lies just beyond the frontier of our understanding. Its implications stretch far beyond the boundaries of Abell 2261. A 2261 BCG is like a cosmic whisper from the early universe, hinting that the story of black holes, those insatiable gravitational beasts thought to dwell at the heart of every major galaxy, may be far more tumultuous, volatile, and unpredictable than we have dared to imagine. If this galaxy did indeed lose its central black hole, the process must have been not only extraordinary but relatively recent on a cosmological timescale. Supermassive black holes, once dislodged, don't simply vanish. They can travel vast distances, yes, but over time, they interact with the surrounding intergalactic medium, with stars, with dark matter, and possibly with other black holes. These interactions create ripple effects that might be faint but still measurable, if we know how to look. And yet, despite years of scanning with some of humanity's most powerful space observatories, including the Hubble Space Telescope and the Chandra X-ray Observatory, we've seen no unambiguous signs. This brings us to a chilling possibility. What if the black hole isn't just displaced, but truly absent, as in, never formed in the first place? While radical, this hypothesis cannot be fully dismissed. Could we be witnessing a completely different evolutionary path for a galaxy of this magnitude? A galaxy that somehow amassed hundreds of billions of stars, merged with countless others, and yet either failed to create or retain the kind of supermassive gravitational anchor we consider fundamental? It would demand a revision of virtually every model we've constructed around hierarchical structure formation. Supermassive black holes are thought to have grown from seed black holes, leftovers from the deaths of the first generation of stars. These seeds, over billions of years, gained mass through accretion and mergers. As galaxies coalesced, so did their central black holes, typically forming binary systems that would ultimately merge, releasing gravitational waves in the process. But what if in this one cosmic scenario, something interrupted the pattern? What if early feedback mechanisms prevented black hole growth? Or what if the dynamical center of mass shifted during a major merger so radically that the black hole never anchored itself, instead being flung into intergalactic space before fully settling? Let's take a closer look at the nature of these potential recoils. When two supermassive black holes collide, especially if they have uneven masses or spins, the resulting gravitational wave emissions can produce significant thrust. We're not talking about gentle nudges. These kicks can reach velocities of thousands of kilometers per second. In theory, that's fast enough to launch a black hole clean out of its host galaxy, especially in cases where the galaxy's gravitational binding energy is relatively weak compared to the impulse. In the case of a 2261 BCG, this kind of event would have left subtle structural signatures, an expanded core, a mass deficit near the center, and perhaps asymmetries in the velocity dispersion of stars. And lo and behold, all these signatures are present. The stars in the core don't move like they do in typical elliptical galaxies. There is no sharp rise in stellar velocity as one approaches the center, which is precisely what you'd expect if a dense black hole were anchoring the gravitational field. Even the light profile of a 2261 BCG is anomalous. In most massive elliptical galaxies, light density increases sharply near the nucleus. But here, it flattens, a plateau of stellar distribution that suggests disruption rather than concentration. This core structure, so vast and so diffuse, implies a kind of galactic scar, the aftershock of something cataclysmic. Still, astronomers are cautious. One problem is resolution. At a distance of around 3 billion light-years, our telescopes can only peer so deeply. Even the best instruments struggle to definitively resolve the fine-scale dynamics at the very center of such a distant galaxy. What we need are next-generation observatories with higher spatial resolution, more sensitivity to faint emissions, and broader spectral range. Enter the James Webb Space Telescope, which holds the promise of delivering the kind of clarity necessary to unravel this riddle. With its ability to peer through dust, detect faint infrared signatures, and resolve fine structures in distant galaxies, Webb may eventually locate the elusive black hole, if it still lingers within a 2261 BCG or floats nearby with its gravitational cloak of stars. Another intriguing avenue comes from gravitational wave astronomy. As detectors like LIGO and Virgo improve, and as next-gen facilities like LISA, Laser Interferometer Space Antenna, launch, we may start to detect the echoes of black hole mergers from billions of years ago. If we can trace one of these signals back to Abell 2261, or a similar cluster, it could confirm the theory of a past merger and recoil event. But let's entertain yet another possibility, one that stretches our imagination and brushes against the speculative. What if the central black hole of A2261 BCG never formed because of dark matter? In standard models, galaxies form within massive halos of dark matter, which provides the gravitational scaffolding needed to draw in gas and form stars. But what if, in this rare case, dark matter dynamics altered the flow of baryonic matter in such a way that the central density never became high enough to seed a black hole? Or what if some exotic interaction between dark matter and normal matter expelled the initial black hole seed before it could grow? While purely theoretical, such ideas are being taken seriously in some fringe corners of astrophysics, especially as anomalies like A2261 BCG multiply. Not because they rewrite physics, but because they expand the edge of what's possible, forcing theorists to consider more diverse galactic histories. Then there's the human element in this story, the astronomers, data analysts, and theorists who pore over every pixel of image data, every spectral line, every faint whisper from this distant beast. For them, A2261 BCG is more than a galaxy. It's a puzzle that keeps them awake at night, a reminder of how little we truly know about the universe we inhabit. It's also a symbol of the joy of the unknown, that thrilling sense that somewhere, out there, nature is playing a game more intricate and unpredictable than any we've yet devised. And perhaps that is the deepest lesson of all from A2261 BCG. It stands as a monument to cosmic complexity, to the possibility that even the most fundamental rules have exceptions, and to the enduring mystery of existence itself. It reminds us that we are not merely cataloging objects in space. We are decoding stories, ancient, vast, and unfinished. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.